or should we wait a few minutes? Okay, so let's start this this mini colloquium. So good morning, everybody. Welcome to the mini colloquium on ultrafast dynamics and transient states in matter. My name is Klaas-Jan Tielroy. I will be chairing the first part of this session. I'm with the Catalan Institute of Nanoscience and Nanotechnology in Barcelona, Spain, heading the group on ultrafast dynamics in nanoscale systems. This mini colloquium on ultrafast dynamics and transient states in matter was initiated by Joaquim Agostinho Moreiro and Harvey Amorin. So briefly about them. So Joaquim, he belongs to the teaching staff of the physics department of the University of Porto in Portugal. And currently he is the head of the polarizable materials and functional nanostructures group of the Institute of Physics of Materials. And he's also the chair of the structure and dynamics of the Condensed Matter Division of the EPS. Harvey Amorin, he's a CSIC tenured scientist here in Spain at the Institute of Material Science in Madrid. So, as I said, this is a mini colloquium on ultrafast dynamics and transient states of matter. This is a very exciting and rapidly growing field of research. More and more groups appearing also in Spain. And this is largely due to the fact that there's more availability of easy to use and affordable ultrafast laser systems. And also a very interesting development is the increasing, ever increasing field strength available in beam facilities to do ultrafast studies. So the idea of this workshop, this mini colloquium, is to discuss latest research, discussing ultrafast changes happening in electronic, magnetic, optical, phononic, vibronic, and spin states in different material systems. So this will be the topic of this colloquium. We'll be going from terahertz to X-ray, so spanning the whole electromagnetic spectrum. And of course, the focus is completely on the ultrafast dynamics in different material systems. So as I said, this is a growing field, a very exciting field, and we're very excited about this mini colloquium, and we hope that in the future this will be having an even larger role in this type of conferences. Okay, before we start, some practical things. So if you have a question, please write it in the chat, and also press the button raise hand. So that means that I can see that you have a question. We propose to do all the questions at the end of the presentation. But if you leave your raise hand button clicked, then that means I can let you ask the question yourself at the end of the session. I suggest that all speakers and hosts and chairs switch off their video except for the speaker that is actually speaking. So let's start with the first speaker. The first speaker is Andrea Caviglia. He is at the Kavli Institute of Nanoscience at the Delft University of Technology in the Netherlands. So Andrea, the floor is yours. Well, the online floor is yours.
Thank you, Klaas-Jan. Can you see my screen?
Yes.
Yes. Great. Okay. Thank you, Klaas-Jan, and thanks very much to the organizers for allowing me to kickstart this meeting. It's very exciting to see we have a mini colloquium on ultrafast dynamics at a Condensed Matter Conference in Europe. And as Klaas-Jan was underlined, this is really a growing field, and it's very nice to contribute to this effort. So the work that I will be talking about has been carried out at the Kafel Institute of Nanoscience in Delft. And I will be discussing work that was performed by Dima Afanasiev as a postdoc in our lab, and Yorito Hortensius for his PhD program. And this work has benefited from theory collaboration from Jaroslav Blanter in TU Delft, that I believe is in the audience, and also from Eric Bousquet at the University of Liège. Before I go into my talk, I would like just to briefly advertise an open position, an open faculty position that we have in our department. Our department is called Quantum Nanoscience, and we have open positions in the areas of quantum matter, quantum sensing, and quantum transduction. So if you're thinking about starting your own lab in the future, please consider Delft. It is truly a great place to do the research. So the broad topic of our research is quantum physics at interfaces. So if we look a little bit broadly into the research in the past decades, we've seen a lot of effort has been put into studying interfaces of semiconducting materials. So in bulk semiconductors, we have relatively simple physics where electrons behave as independent particles. And when you create interfaces out of them, you can trigger new phenomena such as topological types of physics, such as the quantum Hall effect, high mobility electrons, and even realize building blocks for future quantum information. In quantum materials, we start from a bulk picture that is a bit more complicated and certainly more interesting, where we have interacting electrons that manifest as broken symmetries, topological states, and collective excitations. And then when you create interfaces out of them, you can expect rich new physics to emerge. And to visualize a little bit what type of studies we perform, essentially we synthesize atomically sharp interfaces between material A and material B. So the two materials are characterized by quantum mechanical interactions, such as the on-site Coulomb repulsion, hopping integrals, magnetic interaction, spin-Hopper coupling. And then they're also characterized by topological properties arising from their geometric phases. And then by creating sharp interfaces, we achieve a certain degree of control over these various parameters, and essentially create a laboratory for many-body physics, where sometimes we can induce the formation of two-dimensional electron systems with tunable interactions. And the new frontier, as Klaas-Jan was highlighting in his introduction, is really to bring these systems out of equilibrium. So now we can start thinking about these parameters as time-dependent quantities. If we can achieve a driven state of these systems, and therefore gain access to new type of collective states of matter. So in our field, we are trying to allow material design to meet ultra-fast control. And a main focus of our research is to drive low energy degrees of freedom in the systems, in particular phonon modes that we like to keep in a driven state in order to access new kind of behavior. So this is the outline of my talk. I would like to address two topics in this field. The first one we call ultra-fast strain engineering. So in this type of research, we are manipulating the crystal lattice of a substrate material, and we investigate what are the effects on the electronic properties of a thin film that is epitaxially constrained to this substrate. And here I will discuss phase switching, essentially. So how we can induce transitions from insulating antiferromagnetic states to a metallic state. And then the larger part of my talk is on the control of magnetic interactions in correlated materials. So I will show you that by controlling resonant phonon excitations, you can induce a surface control of the magnetic properties of a orthoferrite material. So the material focus of our research are perovskite materials. And so we've chosen perovskites because these are systems that are characterized by strong structure property relations. They're materials that are able to incorporate a great variety of transition metal cations. So we have a structural motif, which is a BO6 octahedral, where B is a transition metal, and a lattice of A-side cations. When you bring these two together in a high temperature phase, you have a cubic crystal symmetry that is able to accommodate a big variety of cations, and to these various cations you have many electronic ground states that become accessible. So only in our lab we study systems from diluted superconductors to multi-insulators, going through various types of magnetic systems. And associated with these various ground states, there are many elementary excitations that we can use to manipulate the properties. So why is the perovskite structure so amenable to this type of manipulation of the electronic properties by the crystal lattice? The essential reason is that the perovskite is able to accommodate cations with various sizes by performing various types of structural distortions that lower the crystal symmetry from the high cubic phase to various low symmetry phases. And so depending on the type of cations that you want to incorporate, you can have a cation that is either too small to realize a cubic crystal structure. So in this case, you will allow for a number of antipolar or polar displacements of the B cation. So that's a typical situation of a type of ferroelectric materials. Or if you're trying to accommodate an ion that is, or for example, a cation that is too small, then you will generate a number of anti or polar displacement of the A atoms. And this is accompanied by also antiferrodistortive motions of the oxygen octahedra. So many type of structural distortion that can be accommodated by the perovskites with various cations. And these are all associated with various electronic properties. So to polar antipolar modes, as I mentioned before, we have associated various types of electric dipolar order. To oxygen octahedral rotations, we can associate spin counting and metal to insulator transitions. To breathing modes, we can associate charge order and so on. So there's a vast space for exploration here. And in our lab, we explore both static control of this type of structural property relations, so through interface engineering. We interface materials with different crystal symmetries and control their structural distortions at the interface, as well as dynamical control, which is what I will talk about today. So through resonant lattice excitation. And as I was mentioning before, the aim is to access states out of equilibrium. And so this is part of a very worldwide research effort, where various types of elementary excitations are being used to manipulate the properties of quantum materials. And so the key aspect is that in quantum materials, electrons act collectively and therefore have associated collective excitations. And these span a very broad range of frequencies, going from the static DC range all the way up to the visible, even X-ray range. So at low frequencies, in the gigahertz range, we find magnons. As we crank up the frequencies, we have density waves and phonons. And then in the visible range, we access excitons and the Motaba excitations in correlated systems and so on. So many of these type of excitations carry a dipole moment, so they couple very efficiently to light, and we can use these to bring the systems out of equilibrium. So this field has been studied has been explored by many groups over the decades, and a typical paradigm was dynamical switching. So people have been accessing hidden phases of matter by accessing metastable equilibrium states. And more recently, the paradigm of dynamical stability has also been explored. So and this is what I will be focusing on today. So the configuration space of these systems, so that the free energy as a function of a microscopic parameter can be manipulated by using laser light, and by manipulating the energy landscape itself, we can think of accessing states of matter that would not be present otherwise. So a driven system can be characterized by minima that are not present at equilibrium. And the key technology that we use is resonant excitations of phonon modes of the material. So this was pioneered by the group of Andrea Cavalieri, and the concept here is to prepare pulses of laser light in the mid-infrared range that are tuned in resonance with a phonon mode. And in order to significantly control the properties of the material, we need to consider what are the interatomic electric fields that we find in matter. So the typical interatomic electric field in a perovskite material is of the order of 100 megavolt per centimeter. So if you want to significantly perturb atomic positions using laser light, you want to apply a mid-infrared pulse that has a comparable electric field. And to give you a sense of the energy scales, the laser field of a laser pointer is of the order of 100 volt per centimeter. So we need a million times stronger electric field than a commonly available laser source. So for this reason, we have to prepare laboratory laser source. And in Delft, we've been working very hard towards this. And here I'm highlighting the work of Dima Afanasyev that has been working on developing a high field mid-infrared source. So we start from the output of a titanium sapphire laser that has about 5 millijoule per pulse. And we use parametric amplification and difference frequency generations to generate pulses in the mid-IR that we can tune in resonance with an infrared active phonon mode in the material. So we start from a laser pulse that carries 5 millijoule per pulse, and we end up with 5 microjoule per pulse at the end. So it's a relatively inefficient process, but still the laser pulses that we obtain at the end are of the order of 10 megavolt per centimeter in terms of electric fields. So a significant fraction of the electric fields that we find in matter. So we can expect to significantly perturb the atomic positions. So our objective is to dynamically induce lattice distortions in the material. And in order to achieve this regime, we need to access an anharmonic lattice response. So if we trigger our atomic displacements with a low amplitude electric field, the best type of response that we can achieve is just an harmonic type of response that rapidly decay. And this is not expected to generate significant perturbations in the electronic properties of the material. On the other hand, if we use a large enough electric field in our excitation pulses, we can think of accessing an harmonic range of the response, and associated with this, we can think of rectification of the phonon field. Therefore, the activation of lattice distortions along a specific Raman coordinate of the crystal. So it's crucial to be able to work with crystals that have anharmonic type of response and large amplitude electric fields. And I'm going to show you a concrete example. So I'm going to show the example of lanthanum aluminate, which is an insulating crystal that is often used as a substrate in oxide electronics. So lanthanum aluminate has a transition from a high temperature cubic phase to a low temperature rhombohedral phase, which is in the Glaser notation a minus pattern of octahedral rotation. So associated with the rhombohedral phase, there's the condensation of two modes, A1G and an EG mode at 800 Kelvin. So at room temperature, this crystal is already characterized by a large lattice anharmonicity associated with this mode instability. So with this rhombohedral transition, you have a condensation of these modes. They become unstable. And here we come to the first measurements that I would like to discuss with you. So this is a measurement of reflectivity as a function of time delay of a crystal of lanthanum aluminate. At time 0, we come with either a mid-IR pulse that is tuned in resonance with a phonon mode of lanthanum aluminate or not. So in blue here you see the phonon spectrum of lanthanum aluminate that has this peak around 15 microns, which is associated with a stretching mode of aluminium oxygen, which is visualized here. So if we excite our material resonantly with these phonons, we see in the reflectivity this pattern of oscillations. So this is an oscillation around 1 terahertz, which corresponds to a oxygen octahedral rotation. On the other hand, if we excite the crystal of lanthanum aluminate off resonance, the specific case at 10 microns, we do not see this oscillation at all, and there is a rapid decay of the signal. So this particular oscillations reflects the activation of this Raman mode, which is visualized in this animation here. So it's at 1.1 terahertz. It's a A1G mode, which is the same one that condenses across the phase transition in the rhombohedral phase. So we indeed activate a displacement and a Raman rotation along this coordinate. So this is important because this type of oxygen rotations in perovskites control locally the bandwidth of the material and the magnetic interactions. So we can expect to obtain an effective modification of the electronic properties of these materials activating this type of modes. The activation of the Raman mode is not the only phenomenon that we observe when we excite the crystal lattice. There is a second very important thing that occurs, which is due to electrorestrictions in lanthanum aluminate. So electrorestriction is an expansion of the lattice parameter of an insulating material in response to the application of a static electric field. And in the case of lanthanum aluminate, if you apply an electric field of the order of 20 megavolt per centimeter to a very thin crystal of lanthanum aluminate, you observe something of the order of a 2% expansion of the C-axis. So when the material is under the strong electric fields, there is an expansion of its lattice parameter, and this generates a strain wave in the system. So this is another measurement performed in our lab of polarization rotation as a function of time, and you see this pattern of oscillations with a frequency in the gigahertz range. So the origin of these oscillations is, as I was saying before, we have an extinction depth of this mid-IR pulse that is penetrating at resonance a few hundreds of nanometer at the surface of a material. The material is experiencing a large electric field and therefore an expansion of its lattice parameter, and this generates a strain wave that propagates through the material at the speed of sound. And as our probe pulse come, the probe pulse experiences destructive and constructive interference with the pulse reflected from the pristine surface of the material as it interacts with this moving phase front. And through this pattern of oscillations, we can extract the velocity of this propagating front, which matches precisely the longitudinal speed of sound of the material, so 4.8 kilometers per second. So in addition to this longitudinal strain wave, we also observe a second peak in the Fourier transform that corresponds to a propagating velocity of a strain front of the order of 6.7 kilometers per second, which is characteristic of the transversal strain of the material. So the transverse acoustic mode has precisely this speed. So This means that in addition to an expansion of the lattice parameter, we also observe a B over A type of distortion of the system, which is a shear strain wave. And our experiments show that as we tune the photon energy of our source, we can redistribute the amplitude of these two strain wave between a transverse and a longitudinal wave. So when we are close to the resonant peak, we have a mainly longitudinal strain propagation, while when we are sitting on the very top of our resonance, the strain, the propagate is dominated by a transverse wave. So there is an interplay between longitudinal and transverse strain that is being generated by this pulse. So to sum things up, there are three phenomena that occur when we take an insulating perovskite and we excite its crystal lattice resonantly with a mid-IR pulse. One is the generation of a Raman mode and a displacement along a Raman coordinate. The second one is a longitudinal strain wave generated through electrostriction in the material. And the third one is a transverse or shear strain wave that propagates through the system, which we believe is generated by the anisotropic type of optical constant of non-thermal. So it's quite peculiar to this particular system. So the longitudinal strain wave is something that is observed also in other materials. The transfer or shear strain wave is something that is quite peculiar to this system. Okay, and this brings me to the application of this approach. So now we will consider a. How much time do I have left, Klaas-Jan? You give me a warning.
It's about 5 minutes.
Okay.
Maybe a little bit more if you need it.
Yeah. Okay. Yeah, I will maybe finish in 7 or so.
That's fine.
Okay. Yeah. So I'll go a little bit fast on this part. So now we can understand this classical dynamics. Let's apply to a thin film. So we have a epitaxial thin films on top of this crystal, lanthanum aluminate. So we consider neodymium nickelate that has a transition from a metallic state to an antiferromagnetic insulating state. And when you grow the neodymium nickelate on different substrates, the epitaxial strain can tune the transition temperature to a very wide extent. And in this work, we have shown that this type of insulator to metal transition can be also driven dynamically by exciting the substrate material as I just showed. So one first observation is that when you start from an insulating state, you can transform the system into a metallic state by exciting the substrate. So you have a variation of 5 orders of magnitude of the DC conductivity in the system driven by the excitation of the substrate. And in addition, when you excite the substrate, the antiferromagnetic order in the thin film is melted, and is melted in an inhomogeneous fashion. So a magnetic phase front propagates from the interface into the film, and so you, through a resonant X-ray diffraction experiment, you can reconstruct the shape of your antiferromagnetic order parameter in the interior of your film, and you find that first the antiferromagnetic order is melted at the interface, and then this paramagnetic state propagates into your film at a speed that is faster than the speed of sound. So you have an order-disorder transition triggered by this lattice excitation. So now the interesting question is, instead of just melting antiferromagnetic order, can we control a transition between order states or states of matter? So we know that magnetization is locked to the crystal lattice via spin-Roby coupling. And if we manipulate the crystal lattice, we can generate a change in magnetic anisotropy, and therefore a reorientation of the magnetization. And this is relevant to the problem of magnetic recording, since the magnetic anisotropy controls the energy barrier between an up state and a down state in a magnetic material. So typically, electromagnetic changes in spin orientation are induced by exciting spin precession, and the precession frequency reflects the curvature of the local magnetic landscape. And if this rotation is large enough, you can switch the material from an up state to a down state, for example. And here we investigated whether by manipulating the energy barrier itself through a change in magnetic anisotropy, we could induce transition between magnetic states. And in our research, we focused on the rare earth orthoferrite dysprosium orthoferrite. So this is an orthorhombic system that has a transition from an antiferromagnetic state to a weakly ferromagnetic state, which is also known as a spin orientation transition. So this is a first order type of transition characterized by the competition between two energy minima and an energy barrier of the order of a few millielectron volt, which lead to this Morin point type of transition. And the idea of our experiment was to modulate the crystal lattice of this material with resonant laser pulses, manipulate the energy barrier through a change in magnetic anisotropy, and induce the spin orientation transition. So first of all, we measure the magnetic potential dynamics by monitoring the spin precession of our systems. So our measurement scheme is a time-resolved Kerr and Faraday rotation. So I will show mainly Faraday rotation measurements. So when we excite the system non-resonantly, we induce spin precessions, which matches very well the Raman data of this system. But now, if we excite the system in resonance with a phonon mode, the spin precession is indeed activated with a larger amplitude, but the frequency of the spin precession itself is being changed. So we see a very large redshift of the magnon frequencies in this system. So this directly indicates that by exciting the lattice modes, we are changing the magnetic anisotropy. If we do the same experiment so this is measured in the low temperature antiferromagnetic phase. In the high temperature weakly ferromagnetic phase, we also observe a modulation of the magnetic potential, a change in magnetic anisotropy through a blue shift of the magnon frequencies. This is a whole data set as a function of photon energy, where you see that as your laser pulses match the phonon resonance, your magnon frequency can be either red shifted in the low temperature phase or blue shifted in the high temperature phase. So this directly indicates that we have changes in the magnetic potential. So these changes occur very fast. So in a few picoseconds, you have renormalized your magnetic potential, and then this relaxes back to the equilibrium phase in a time scale of the order of 100 picoseconds. And so we have direct access to an out of equilibrium state in which we have generated a metastable magnetic state with a softer potential through a change of the magnetic anisotropy K2 constant of the material. Now the question is, can we also induce a transition to the competing weak ferromagnetic phase? And the answer is yes, but this requires a minimum amount of fluence. So if we excite the system gently with low fluence, we observe harmonic spin dynamics. But as we crank up the laser power at the phonon resonance, we start to observe an anharmonic response, a nonlinear spin dynamics, and the emergence of a net magnetization in the system measured by the Faraday rotation. So this indicates directly a transition from the antiferromagnetic state to the weakly ferromagnetic phase. And the threshold of this process is something of the order of 4.5 milliwatt. So what is the difference between this approach, this we call phonomagnetism, and the conventional photomagnetism? So this is the same material being excited by a charge transfer excitation, as you see in green. And this is our phonon pumping approach that you see here. So indeed, when you excite the charge transfer, you do excite spin precession and then the emergence of a magnetization through a mechanism that I discussed before. But this relies on heating of the material, and it takes something of the order of 100 picoseconds to occur. When you excite the material directly with the phonons, you can induce the transition to the weakly ferromagnetic state within the first cycle of the spin precession. So in a few picoseconds. So this I will skip, and this brings me to my conclusions. So I showed you that by addressing directly resonantly the crystal lattice, you can induce ultra-fast changes in the magnetic interactions, and this can drive spin orientation type of transitions between competing magnetic phases. Okay, and now I'm ready to take your questions. Thank you.
Thank you, Andrea, for a very, very interesting talk.
Yes.
I have not received any questions via the chat yet. So I suggest that if anyone has a question, just press the button, raise your hand, and I will give you the microphone so that you can ask your question. So let's see if anybody wants to raise their hand. If not, maybe I can start with some questions. So just a few technical questions. So this was all measured at room temperature, or was this also done at low temperature?
Okay, right. So the measurements of the spin orientation transitions, they occur. So the transition occurs at 50 Kelvin. So we studied both below and above this phase transition. So below the spin orientation transition, so in the antiferromagnetic state, we observe this softening of the potential, and then the switching to the weakly ferromagnetic state. So you need to be below 50 Kelvin for this phenomenon to occur.
Okay. Okay. Clear.
Yeah.
I see there's a question from Agostinho. So let me give him the.
May I?
Unmute it. Yep.
Thank you very much, Andrea, for your nice talk. I have a question. Did you try to prove the ultra-fast control of magnons in dysprosium ferrite?
Yes. So this is this type of work that we've done here, where we were manipulating the frequency of the magnons by acting on the crystal lattice. Yeah. So that's
And are you planning to do this study in other rare earth ferrites?
So we are planning to study. So now I've shown this as a surface type of phenomenon. I didn't discuss this in detail, but this is something that occurs in the first 100 nanometer of the surface. And now we are planning to study the system in an ultra thin form. Mm-hmm. To have also strain control of the ground state of the system. So combine both strain control and ultra fast strain to manipulate magnetism.
Okay, thank you very much.
Okay, I see there's a question from Astita, who I will unmute, so you can ask your question.
Yeah, thank you very much. And it was really nice talk, and I was waiting from morning to listen. So my question is it possible to reveal changes in spin canting or the magnetic behavior of, for example, system like bismuth ferrite by exploiting this technique, what you have shown, which is quite fascinating. And so
yeah, I agree with you. Yeah, bismuth ferrite is an ideal candidate for this type of study, because there you also have a ferroelectric polarization and possibly electromagnons in the system. But I believe that system will be particularly interesting to study by resonantly exciting the ferroelectric polarization itself. So rather than going through this stretching mode as we are doing here, at exciting a 20 terahertz mode, you also have this soft mode associated with ferroelectricity, which there are at 1 terahertz. So if you can do this experiment with a strong terahertz source in that range, I think it will be very interesting.
What about to do measurements with such nanopowders? Means they are in nanoparticle regime, like within 50 nanometers, but they are in powder form. So what are the suitable conditions for such devices?
I see. So powder forms, I think that what you will see will be quite complicated. So here we rely crucially on the fact that we have a long-range crystalline order and some specific strain at equilibrium that then we perturb. With in a powder form, I do not know what would happen, to be honest. Probably it will be complicated.
Okay, and to have a solution or dispersion?
Yeah, it's an interesting point. We have not done this type of experiments in dispersions or solutions,
Okay.
and I think it will be an interesting thing to study.
Okay, I think we need to move on to the next speaker. So let's thank Andrea again very much for this very interesting talk. So the next speaker is Stefan Kaiser from the Max Planck Institute for Solid State Research in Stuttgart, Germany. So please start your presentation.
Okay. Hello everyone, can you see my screen?
Yes.
Yes,
Okay.
it's not full screen yet.
So now it's full screen?
Perfect, yes.
Okay, perfect, yeah. Thank you very much for the invitation and the organization of this mini symposium. And yeah, I want to present on our efforts on establishing Higgs spectroscopy in superconducting cuprates. And that is work that is carried out at my group that is located at the Max Planck Institute for Solid State Research in Stuttgart and also at the University of Stuttgart. And the work presented here is a very close collaboration with the group of Ryo Shimano at the University of Tokyo and the high field terahertz group at the Helmholtz Center Dresden-Rossendorf. And so this is a project we have embedded in the Max Planck UBC Uni Tokyo Center for Quantum Materials. And here you see the main players of my group and Ryo Shimano's group, mainly Hao Chu and Min-Jae Kim in my group. Then from the Helmholtz Center Dresden, where we carried out experiments at the high field Telbe terahertz source. Here we worked together with Sergei Kovalev, Jiwang, and then also Michael Gensch, who back at this time was in Dresden. We have theory support in-house in Stuttgart by Lukas Schwarz, Dirk Manske, and Andreas Schnieder, and a lot of support from the sample side, characterization, linear properties, optical spectroscopies within the thin film group of Gennady Logvenov and the department of Bernhard Keimer here in Stuttgart. And we also have collaboration with the group of Jan Gallet on related materials in this. Before starting, so what is this Higgs spectroscopy of superconductors? So in principle, these Higgs modes, they fall into the class of collective modes, similar to what Andrea has said already before. We know we have the collective excitations of a lattice, which are phonons, of spin waves, which we can characterize as magnons. Of the electronic system itself, we have plasmons. And all of these modes, as we have seen before, okay, they have either a dipole moment or with some nonlinear couplings, we have easy ways to directly drive these modes in a light-driven experiment. However, what about the collective modes in superconductors, which are the Higgs mode of a system? Because here we have a problem that these modes typically don't have dipolar moments, so the Cooper pairs cannot directly excited by light. And if we usually look at superconductors with optics or with tunneling spectroscopy, we can only get a hold of the real part of the complex superconducting order parameter. And then usually what we map out is the function, the gap size as a function of temperature in a system. And then from spectroscopies, we can learn something about the structure of the gap. Is this a full gap? Is this only a momentum space, only a partially filling gap? And then usually we have to take a full set of tools to really fully characterize the order parameter of a superconductor. For example, if you want to have the K-space, we would even need to use ARPAs. And then if you want to measure, for example, the phase of a superconducting material, then we even have to involve experiments like tunneling at Josephson junctions and so on to see effects of the superconducting phase. However, our goal is to really directly access the collective modes of the complex order parameter. So if we think of the complex order parameter of a superconductor and we draw now the free energy surface as a function of this complex order parameter, then this gives rise to this famous Mexican hat. And here we have two types now of collective excitations. One would be an oscillation here of the phase that is dissipationless. So in that sense, that is the famous Goldstone modes in a system. And the oscillation here along the rim of this Mexican hat, these are oscillations of the real part of the order parameter. So this would be really an oscillation of the what we measure as a gap size in the system. And these are the famous Higgs oscillations in the system. The question is now, how can we excite these? And the problem is, since we can't directly drive these Higgs modes because we can't shake this potential around, one option is that we quench this potential. If we come with an ultrafast light pulse that quenches this potential, then we are here in a displaced position, and then we can start oscillating around this new equilibrium position. So that is something that we are showing here. So we are in this equilibrium case. So we come with an ultra short light pulse, we quench this potential, now we are in this displaced position, and then the system starts oscillating around this new position. So for the people that work in the field of coherent phonons, that looks really very much like an impulsive or displacive excitation of a coherent phonon. The only difference now is that the oscillation frequency here is not given by the phonon phase vector, but the Higgs theory tells us that this eigenmode here is now oscillating with 2 times delta of the superconducting gap. And experimentally, in an S-wave superconductor, these kind of Higgs oscillations were first seen by Ryo Shimano's group back in 2013 on niobium nitride, which is an S-wave superconductor. And what they did, they were exciting the system with an ultra-short terahertz pulse. And then, so this terahertz pulse makes sure that you quench this condensate without exciting hot quasi-particles that would screen or response. And then they were probing this response with a time delayed terahertz pulse. And then they found here some characteristic oscillations after this quench of the potential. And then depending on the strength of this quench, so with increasing fluence, they quench this potential more and more. And what they see then is that this oscillation gets slower and slower. And they could show that this oscillation is always following this transient size of the gap of 2 delta. And that was the first fingerprint for a Higgs mode oscillation that was excited in a superconductor. A second possibility for exciting or controlling Higgs mode in a system is now not to make a quench of the potential, but to go to the system with a low frequency terahertz pulse that is below the superconducting gap. So in the linear regime, we have no excitation of quasi-particles. And then one can show that the superconductor will respond with a 2 omega response to this driving field. And then if these two come in resonance, then the superconductor emits a characteristic third harmonic in the system. And this physics one can understand in the so-called Anderson pseudospin model. So if we would think of a normal metal, and there we would now say every occupied state up to Fermi, we would assign now with a pseudospin up. So a spin up is showing us an occupied state, a non-occupied state we would assign to a spin down. Then we have an effective spin 1/2 system that we could put now the driving field, we could act as a pseudomagnetic field, and then we can use Bloch equations to calculate the response of our metal. This is something that is very well known. If one translates this now to a superconductor, then we know in the BCS state, we have this superposition of occupied and non-occupied states. So in principle, our spin here, our pseudospin will tilt in this system. And this is something we can now map to this Bloch sphere, this state, and now we can evaluate Bloch equations, so to say, and that is then under the driving of a multi-cycle field, this pseudospin now starts to precess. And this is something, yeah, the coupling to the light is done by this E times the vector potential, but now the Cooper pair basically is two bound electrons, so we have to have a momentum transfer of E times A per electron, so we have E square, A square, and that is something that explains us why this 2 omega response happens of the superconductor. And then in the following, if we now take this 2 omega response and bring this in resonance with this omega response, then we can calculate, for example, the nonlinear Josephson currents in the system, and they show us that we are reaching resonant behavior of a characteristic 3 omega response when this driving frequency gets into the resonance of the Higgs mode. Sorry, the driving frequency, when the 2 omega gets into the resonance of the Higgs mode. And experimentally in the niobium nitride, this was also shown. So here you see this response of the system above TC in black, and then below TC, you see here really at above TC, there's only a response at the driving frequency. And then when the system becomes superconducting, there's a characteristic third harmonic generation that comes out in these systems. And looking at this as a function of temperature, one indeed sees, okay, there is really a resonance behavior when this 2 omega equals 2 delta resonance condition is met. That is where the superconductor has the highest efficiency for the generation of this characteristic third harmonic generation. In the following, we are now interested to really look at the Higgs modes in unconventional superconductors. And here, most important are the systems that don't show this conventional S-wave superconducting systems where we have an isotropic gap. For example, we are interested in D-wave superconductors like the high TC superconducting cuprates, where we have a momentum dependent gap of this system. And this has severe consequences for how Higgs modes in these systems show up. For the one in the S-wave superconductors, in principle, the only possibility for oscillations are full symmetric oscillations in the system, which we could say these are in a phonon sense, we could label them with an A1G type of oscillations. However, we could show that in these D-wave superconductors, depending now on your momentum transfer of the system, you could do now different symmetry quenches to this system, and in principle that would allow you to access different kind of oscillations, like a full symmetric one, but also an antisymmetric one of the system. So this would be like a center of mass and the relative motion of the system, but depending on the quench of your system, you could also set a rotation oscillation or a clapping oscillation of these superconducting lobes. So in principle, this Higgs spectroscopy in some sense is an analogy to the phonon spectroscopy for the collective oscillations of a lattice, but now we have the different Higgs oscillations for the eigenmodes of the superconducting condensates. And as much as we can learn from the phonon oscillations about the dynamics of a lattice, we hope now to learn from the Higgs oscillations for the dynamics of the superconductor itself, including if we see the Higgs oscillations, if we know the spectrum of these Higgs modes, we could even call back and figure out what kind of order parameter is oscillating in the system. However, there is one problematic part. In these S-wave systems, we have seen, okay, we had these nice ringing oscillations after the superconducting, after quenching the superconducting condensate. And the reason is because in an S-wave system, the superconducting gap is open in the whole momentum space, and hot quasi-particles are always separated from the superconducting condensate by a full superconducting gap. However, in these D-wave systems, we see already momentum dependent. We have a change of the superconducting gap from 0 up to delta max in the system. So that means inside the gap, depending on momentum, at every energy, we will find some hot quasi-particles in the system, and that will lead already to a strong damping of superconducting Higgs oscillations in the system after a quench. And yeah, the idea now is, okay, how is it now possible to really see different Higgs oscillations for different kinds of order parameters in the system? And there you have to now tailor your excitation pulse to a certain symmetry. And from this, you would get then a certain Higgs spectrum for your oscillations. And then depending on this Higgs spectrum, you could then map back to the oscillating order parameter of your superconductor in the system. And the goal here is now to show this for this important class of the D-wave superconductors, which is this dx square minus y square symmetry. Of course, in this case, we already know the oscillations, but now we have to show, can we really drive these Higgs modes in this system? And as I said in the beginning already, the first thing we have to take into account is this strong damping, where in an S-wave superconductor, we have these long-lived oscillations in the system. However, in a D-wave system now, you see already these modes get really, really broad already in a theoretical simulation of the system. And in addition, additional modes may show up due to these different symmetry channels that we can excite in this material. And one way out is to drive these Higgs modes in the system. So instead of quenching the condensate, we will use the second approach to constantly drive the superconducting Higgs modes with a multi-cycle pulse. And there we also expect to see now, instead of this sharp resonance, something that is heavily smeared out due to the damping of the quasi-particles. At least if we look at this in theoretical evaluation of Higgs mode response within this pseudo-spin model that I've described in the beginning. But now jumping really to first experiments. So if we perform now, for example, an attempt to quench the superconducting condensate, for example, on a visco sample. So we come with a very short high field terahertz pulse, and then we probe this optical response and we try to look for transient oscillations of the system. Then we don't find them in, for example, optimally doped visco of these materials. All oscillations that we find here are only the 2 omega oscillations from the driving field whilst the pump is there. But there is no oscillation that can be found here on the transient response. So in the following, we will stick now to this drive of the system, and we will now look at different classes of superconductors, and we are taking both single-layered LSCO samples, but also double-layered systems like DIPCO or YBCO superconductors. And we will stay now most of the talk in the optimally doped regime, so that for the people that work in superconductors, this is a regime where we don't expect a strong influence of competing orders like charge density waves, pseudo gaps, and so on. So here we want to look at the pure superconducting response of the material. And you see here, these are high quality thin film samples with very sharp and high TCs for the respective classes of these cuprates. And our experimental setup is here. So we are going to this high field terahertz Telbe source at the Helmholtz Center Dresden. And then we are tuning this undulator now to 0.7 terahertz in our experiment. And then we set up an experiment that we have full control of the polarization state. We also clean up the beam with bandpass filters. And then we go with a long multi-cycle 0.7 terahertz beam to the sample, and then we want to perform spectroscopy on potential third harmonic generation of the system, and also there we can map out the full polarization state of these generated lights. And this is now the experiment on optimally doped LSCO. So here is the transmitted terahertz pulse, now at 90 Kelvin, so at temperatures above TC. And what you see here basically is only the transmitted 0.7 drive field of our terahertz source. If we now cool down the sample, then you see here on top of this drive field, now here in the back, you see already fast oscillations that are being generated. And these are indeed the third harmonic generations of the superconducting state. So now we can filter these signals, and then we can extract the fundamental and the generated third harmonic generation in the system. And now we can plot this, for example, as a function of temperature. And if we look at this now, for example, here for the optimally doped dysprosium, then we see here below TC, this is the black dashed line here, we see a strong onset of these third harmonic generation as we've expected. And yeah, now on the first view, this might look like, oh, there is a very sharp resonance in the system. However, what we have to take into account here is, of course, as soon as the sample becomes superconducting, then also a huge screening sets in. So we have to correct this third harmonic generation with respect to really the local field that is in the superconductor itself. And if we do so, then you see this third harmonic generation is really setting on strongly only below TC, and you see there is no strong resonance feature on this on these trays, which is in full agreement of heavily damped Higgs mode that now has resonance conditions, because we have a gap that is continuous from 0 to delta max that is basically setting in below TC. If we look at this now for the other samples, we find very similar responses for all of these samples in the system. So far what we see is, okay, indeed, we can drive very, very strong Higgs modes, and we find that these Higgs modes are heavily damped in this material. The question is now, how strong is the damping? And for this, we now take a very, very simple model. If you want to figure out how strong is a system damped, then we can think of a normal harmonic oscillator. If you think of a superconductor of a normal harmonic oscillator, and then we know, of course, these in a heavily damped system, this resonance of the amplitude becomes smeared out strongly if we start damping. But what is a very good tool to measure the strength of the damping is to look at the phase response of such an oscillator. Because at an underdamped oscillator, the phase response makes a pi phase jump from low to high at the resonance frequency. And if you have a heavily damped system, this pi phase jump smears out here. And what we are doing now is we want to look at the phase response of this third harmonic generation with respect to our driving field in the system. So we are interested now, what is the relative phase of this third harmonic generation with respect to this fundamental driving frequency. And the problem in our experiment is it's really difficult for us to tune now the frequency of the light continuously in these kind of experiments. So what we are going to do is, by temperature, we are going to tune now the resonance frequency of the gap. So basically we are changing the resonance of our oscillator now with tuning the temperature in the superconducting system. And then if we would sit here at this point, for example, that would be now our 2 omega equals 2 delta resonance condition in the system. And then if we are at temperatures below this, this would really correspond to a drive of our system below the resonance frequency. On this side, this would really be like a drive above the resonance frequency in our system. And if we now do this experiment and we look at this dysprosium, then we see indeed, okay, above TC, there's only a smooth evaluation. Maybe there's a very tiny jump of the phase of the system. But then a big surprise was happening when we tuned the frequency, the temperature even lower. because then we found here at temperatures far below TC a very prominent phase jump in this material. And this is a phase jump that is happening in all of these materials. And there are two important observations of this phase jump. One of this, it looks like if you go to the unnormalized data, this phase jump is happening here at this shoulder or at this notch of this THG in this system. So it looks like this is very close to some kind of an anti-resonance. The second observation is, I told you before, an oscillator usually has a phase jump from low to high, but here our phase jumps from high to low. So the opposite direction of a normal expectation. So this is what an oscillator, a normal simple oscillator would do, but here somehow it looks like our oscillation has an anti-resonance. So that rules out that this phase jump comes from the Higgs mode itself. The question is now, what is this? And so we have now a new mode in the system. So either we have a new mode that is oscillating together with this heavily damped 2 delta Higgs mode in our system, or this mode is even coupled to this 2 delta Higgs mode in the system. The question is, how can we figure out what is the difference? So we can use this independent oscillator model, and then we can model this in a way that we mimic our experimental data. But for this, then we would have phases that would go from low to high, both for the heavily damped 2 delta Higgs, which has basically a very broad phase jump, and the new mode that would be underdamped, that would give a sharp phase jump, but from low to high. However, if we would take a coupled oscillator model and would model something like this, then we would really get a phase jump from high to low about the anti-resonance condition of these two coupled oscillators. And that is observation that is very, very close to what we find in our experiments. And of course, this looks maybe a little bit strange to you if you work with oscillators or with phonons in your system, because keep in mind here we see intensity on phase over temperature in the system. If you go back to the model behind that has the oscillators, you really see this is really a model that has two oscillators. One broad oscillator of the Higgs mode dashed here in the background, and a very sharp new mode that is here inside the gap. And then really amplitude shows two peaks with an anti-resonance, and that is exactly where the phase here in blue shows these drop around this frequency. The question is now, okay, what is this new mode in this system? One possibility is that really this mode would be one of these non-AG Higgs modes in the system. Other possibilities that were already now discussed in the literature is that in some superconductors, you could have subdominant pairing channels in a system. So you could have other order parameters in the system, and they could really, like an exciton, give now in-gap states, which are called so-called Badasis-Schriefer modes, if they would be driven. For example, in pnictides, that would be a very famous example. However, in the cuprates, this mode is very, very unlikely. Another possibility would be strong coupling to other modes. For example, in S-wave systems, one could directly think of phonon-mediated scenarios. However, in the cuprates, probably the magnetic resonance is one of the most famous things that we could think of, because also the energy of these modes are very, very close to the superconducting gap. And therefore, now we also started to do a doping-dependent investigation of this. And this is now this optimally doped LSCO that we've seen before. And if you go to the overdoped regime, what we can see is, maybe just look here at the phase jump of the system. This phase jump starts to smear out more and more if you go away from optimally doping towards the overdope, and it goes fully away in the fully overdoped regime. And also in the underdoped regime, basically this phase jump fully disappears. And that is already ruling out some scenarios like the simple phonons or whatever, or at least it would be difficult to understand this with simple phonons, but these magnons, for example, are a big player that are still in this game, because the phonon modes, that should still have very, very strong resonances in the system, while these magnetic resonance modes usually are known to smear out and disperse as soon as you go away from optimally doping. But now future experiments really have to show what's really going on in these materials. So next steps would be now to also do magnetic field dependencies of these, and maybe at the very end, or if someone is interested, I can show first hints on this, what a magnetic field dependence of these phase jumps would look like. And a big discussion, of course, that comes up if you're dealing with high field driven superconductors is always, is this response really due to a superconductor itself, or is this something you're exciting hot quasi-particles, and then if you just drive a very strong current, then there is no reason why this current should not show up in a THG response as well. And for this, we have performed also now a full polarization dependence of this state. And then you see in this LSCO and DIPCO, in principle, in these systems, we have no polarization dependence of the THG response, which is a strong fingerprint for Higgs response, because if this would be a current, this current has to obey the symmetry of the crystal, and that should have a very strong dependency with the polarization of this state. For example, if you have a very bad superconductor where you have a lot of hot quasi-particles in the system, then indeed you find these strong dependencies in the polarization state of a system. And then also this whole phase jump phenomena basically disappear, or here you really see now a phase jump in the opposite direction due to a coupling with plasmods in the system. And the second important fingerprint is the dynamical response of the system, because so far I only told you on this third harmonic generation, but this is based on this 2 omega drive of the superconductor itself. And the question is, can we see this as well? And this is now a terahertz pump optical probe experiment of the transient response. And then you see on top of this electronic response, you see very prominent oscillations. And if we evaluate these, then we see we have omega and 2 omega oscillations. And these omega oscillations, which indeed could be driven currents, we see at TC, they become heavily screened, as we would expect for any current in a superconducting response. However, our 2 omega responses really become heavily enhanced below TC, which shows they are not due to screened currents, but they are really due to driven Higgs oscillations in the system that set in below TC in this material. The question is now, of course, okay, why are there 2 omega responses even above TC in this system? And that is something that brings me to the last interesting point here now is, if we compare, for example, now the intensity of this THG, one can show that this is linked by the forced power to the superconducting gap. And if we plot now here the superconducting gap measured with linear measurements, and we map on this now the order parameter evaluated from our Higgs spectroscopy, then we see, okay, we are mapping this pretty well below TC, but above TC, we are now mapping a finite response of the Higgs. And the interesting point is, this finite response, we map in the different classes of the superconductors somewhere up to the temperatures where typically the Nernst effect is seen in the system. And that brings us to the point that now our method, also above TC, is also, yeah, capable of finding something like we would interpret as a possible finite pairing amplitude. So our method is also now a new tool that we could use to evaluate the responses in the pseudogap regime, which is, yeah, one of the big mysteries in this whole high TC field. And this basically brings me to the conclusions of my work. I've showed you that with these high field nonlinear terahertz drives, it is possible to excite and drive Higgs modes now also in cuprate superconductors, seen here by characteristic third harmonic generation. And then by not only looking at the amplitude response, but also of the phase response, we can see now also how this mode is now coupling 2 different modes in the system. The big question is now still, what is the nature of this mode? And last thing is now also this method gives us now a new powerful tool to evaluate also finite pairing amplitudes in superconductors that are happening even above TC. And yeah, maybe in a brief outlook. I'm not sure how I'm doing with time.
Yeah, we're running out.
Running out. Okay, then maybe I leave you with these conclusions, and then I'm happy to answer questions.
Very good. Thank you, Stefan, for a very, very exciting talk. So let's open the virtual floor for questions. Again, there's not yet a question in the chat, but if anyone wants to ask a question, please let me know and I will give you the mic. Okay, there is a question. Yes, please ask your question.
Yes. Yeah. Can you hear me?
Yeah.
Okay. Yeah. Thanks, Stefan, for the nice talk. Yeah, I have actually a couple of questions. One is more like technical. It's about your renormalization of the resonance, which is no longer resonance, but like rather a jump. Like, how do you actually obtain this normalized data, and in order to account for the overscreening in the superconducting phase?
Yeah, so one thing that we do there is, in principle, we are measuring also linear properties. Let me see. For example, here, this is the transmitted fundamental harmonics, where you then also see that this has strong drops at TC. And in principle, we are normalizing basically to this. But on a second one, we also have the full linear optical properties of the material, and we can also correct for this. And we have taken care here that we are still in a non-perturbative regime, because what we don't know are, of course, the transient non-linear optical properties in the material. So in that sense, the safest way is to take the real measured third harmonic of the system. And since it's a thin film, we can assume that in principle, the local field within the thin film is more or less constant over the film, so that we don't have to take into account big changes there.
I see. And in the data, if you look at the oscillation at the different condition, like by changing the temperature, could you also see some phase shift there?
Yes. So that is something I haven't said here. Of course, also the linear response shows a certain phase shift, and this is corrected already here. So what we do is we shift before evaluating the relative phase between the THG and the fundamental, we make sure that the linear shift of the fundamental is already compensated. This is the one way. And the second way is, of course, you can make the Fourier transform of your pulses, and then you take the relative phase between the fundamental and the TH. And both of these give us the same result. Okay. And also here, in this case, we have taken care that, because of course it's a thin film model, so you could have many, many phase shifts at the different interfaces. So we also have taken care by taking the full Fresnel equations of the linear properties that we have measured to make sure that this phase shift really comes from the relative phase between the fundamental and the THG itself, and not from a switch of the refractive index at the interfaces, for example.
Yeah, maybe just very quickly. So could you imagine to apply this spectroscopy also to other low energy collective excitation? So I'm thinking, for example, of exotonic insulators, where you also have like condensed pair.
Of course, collective modes itself, that is something, whenever you can drive them, they would give you these kind of responses, and you can see all kinds of couplings. However, to really figure out the Higgs response itself, you need the Meissner effect. You need the Anderson-Higgs mechanism. That means in a conventional system like an excitonic insulator, you still would have phase modes or whatever, potentially, where your Higgs mode can decay into. However, in the superconductors, we know the phase modes are lifted up by the Anderson-Higgs mechanism to the plasma frequency. So the Higgs mode itself cannot decay into any phase modes. And that is what gives the nature of this peculiar response in the cuprates. So you would really need a U1 symmetry system with an Anderson-Higgs mechanism for this to work. But the other points, that if you have all the collective modes, like also an amplitude type of mode, for example, in the excitonic insulators. And there you would see couplings. All of these evaluations you could do in an equal way.
Mm-hmm. Okay, thank you.
Okay, if there's one really short question, we can take it. If not, then we will move on. So does anyone have a very short question? Let me know in the chat. If not, then let's thank Stefan again, and we'll move on to the last invited speaker of this session. So the next speaker is Simon Wall, who is both at ICFO in Barcelona and also at Aarhus University in Denmark. So please, Simon, start your presentation.
Okay, can you hear me, and can you see the presentation?
Yes, perfect.
Great. Well, sorry. Thank you for the invitation to be here and the introduction. So my name is Simon Wall, and as was said in the introduction, I recently moved to Aarhus University. And just in case if anyone's interested, we probably will be hiring very soon, so please get in contact. So my talk today is probably has a bit more in common with Andrea's talk at the beginning, and it's looking at phase transitions and the role of vibrational coherence or otherwise in these phase transitions. So over the last 10 decade or so, I mean, one single decade, 10 years, there's been a huge increase in the number of papers reporting light-induced phases inside of materials, including metal insulated transitions in the manganites, charge density wave, spin density wave states in the pnictides, and most recently superconductivity above much higher temperatures than found in equilibrium. And these are really exciting and important discoveries, but we really still don't know in many cases how these are really understood and how they can be controlled. And so at the moment, I like to think of these stages a little bit like this photograph here of this car which is driving around a loop-the-loop. So if you drive your car fast enough, you can get it to drive upside down. Okay, so normally if you're going along slowly, your car would get to the top of the loop and then fall down, and you'd have a problem. But if you go fast enough, you can complete this loop-the-loop. And this is quite a spectacle, and many people in this crowd you can see have been pretty impressed by this. But at the end of the day, it's not very useful. We cannot start driving on the bottom of a bridge and double our bridge's capacity, which would be a good thing. But with it was not going to work for in real life. And so what we would like to do is try and understand how we can take such a phenomena like high temperature superconductivity and extend it so that we can use it in a practical situation. And so one of the issues is that we still don't really understand how to completely characterize and understand these phases and to understand how the system moves from the ground state into a metastable state. And often we draw a picture like is shown on the right-hand side here from this excellent review of quantum materials, where we take the system which is on some free energy surface, which in this case is a two-dimensional surface, and the light pulse moves it along that surface. And today I'm going to tell you about our results on trying to understand this surface, what it is, and if we can draw such a picture. So the material I'm going to talk about is a material that's been studied a long time, both in equilibrium and in non-equilibrium, which is vanadium dioxide, which has a thermal metal to insulated transition. So I'm not going to be talking about accessing a new hidden phase. I'm going to be talking about just what happens when we shine light on this known phase, and hopefully we can figure out the processes that are going on here and how they may influence the access of metastable and transient hidden phases. Okay, so vanadium dioxide is quite, in some sense, it seems quite a simple system. We have a high temperature metallic phase, which has a near sort of cubic symmetry. And when you cool down the system becomes an insulator. And this insulating phase transition occurs at the same time as the structural transition, in which the vanadium ions go from the high symmetry positions, they dimerize and then they twist, and this opens up a band gap. And as you can see here is a nice plot of the simultaneous nature of these transitions, where we have diffraction and resistance measured simultaneously in the bottom right-hand corner. And we see that less than 0.001 Kelvin, these transitions occur together. And the very sharp nature of this transition indicates that it's a first order phase transition. Okay, so we're going to investigate the reverse process, which is using light to drive from the dimerized state to the rutile phase. And I'm going to tell you about how we've been working towards watching how this happens and investigating whether vibrational coherence can play any role. Okay, so before I start, I'm going to draw a picture which has been shown already twice before, and in this case, for the case of vanadium dioxide. But I think it's important because we need to know how we define a phase. And so VO2 is a little bit more complicated because it contains the dimerization and the twisting. So you could think of the atoms. So you could think of those as the two axes on the potential energy surface, 2D potential energy surface I showed earlier. For the purpose of the discussion, I'm going to think of just a one-dimensional case, which is a dimerization. And so we have VO2 in this case would be represented by a linear chain of vanadium ions, which are equally spaced in the high temperature phase. And when the system cools down, there is a dimerization, which causes a symmetry breaking. And the system has to choose how it dimerizes. So it can either dimerize with pairs forming starting on this unit cell, or it can start with a pair forming in the next half unit cell over. Okay, so this dimerization would be characterized by a distortion delta. And this delta has a phase, plus or minus, depending on which one of the twins it chooses. So this is a little bit like the phase that Stefan was talking about in the previous talk. And these are, but this is pinned to just two values, positive or negative. And it corresponds to just crystal structures which are translated by half a unit cell to each other. Okay, so the system cools down and we have a dimerization. And the whole system can be described by this parameter delta, which is how far the atom moved from its equilibrium position. So here we have a positive delta and a negative delta. So I'm calling this Q is equal to delta. And here we have a negative delta and a positive delta, which I'm calling Q positive. And these are the structural order parameters. And this is what we want to track if we want to understand how this phase transition occurs traditionally. Okay, so first of all, before I talk about how we actually measure that delta in a structural transition, I want to talk about what we know from an optical point of view. Okay, so this is a first order phase transition. And I think as Andrea showed in his talk, when you pump this system, there is a very clear threshold behavior in the change in the reflectivity. So this is the reflectivity changed after 1 peak second. And you see that for low fluences, the change is relatively small. And as soon as you hit the critical threshold fluence, there's a very large drop in the reflectivity, indicating the phase transition. Okay, and then it starts to saturate at higher fluences. If we look at what's going on in the low fluence regime, we see phonons, as many of you may be aware. These phonons oscillate, and there are actually quite a few phonons present in the system, but the main two occur at 5.7 and 6.7 terahertz, and these correspond to the bending and the twisting of the vanadium dimers. I've drawn them on the right here, separated from each other, but they're actually occurring on all the atoms within the unit cell in the same way. So there's a dimerization and the twisting. And as Stefan talked, mentioned, these can be just considering the system evolving on the free energy surface. And so this would again have to be a two-dimensional one, but the ball is rolling backwards and forwards inside this new potential. Okay, so when we excite the system harder, we see a loss of these coherent phonons. And the reflectivity instead shows very different dynamics. So just a small, a slow and gradual increase at this particular case. It depends a lot on the fluence and the wavelength. But most importantly, we see there's no phonon modes in the system anymore. And then the question we've been asking, I've been asking myself since 2012 anyway, is whether or not these oscillations, they carry on, but to drive the transition, but we can't see them, or if something else is going on. So at some point, when we drive the system optically, we can't see the phonons anymore, but we don't know really what's happening. Okay, so one possible scenario is that they undergo a transition along sort of these lines, so we can see if we carry on the twisting motion from a small amplitude to a larger amplitude, we'll eventually align all the vanadium dimers. We can also undimerize, and if we undimerize by a significant amount, we can map the structure back onto the the rutile phase. And of course, this untwisting and undimerization doesn't have to go in a stepwise manner, most likely go simultaneously. And the question is, are we doing this loop from the M1 to the R phase in this continuous like motion that I suggested here, or is the system taking another pathway? Okay, so the summary, oops, that's a repeat. Okay, so how do we determine this? And so what we have to do is we want to measure the structure. So we have to go to a probe which is measuring the structure, which is X-rays. And traditionally, people have looked at this process using Bragg scattering. So we all know that we can use Bragg scattering to determine the structures of crystals. And if you go through your maths, which I'm not going to do here, you can work out quite easily for a dimerized system or a dimerizing phase transition, there are two types of peaks. There are even peaks, which are present independent of the value of delta, independent of the magnitude of delta. And these are the peaks that correspond to the high temperature phase. And then there are odd peaks that are present only when the system is dimerized. Okay, so as you increase your lattice distortion, you'll see a series of peaks growing with increasing intensity, with a series of peaks that are decreasing with intensity. Okay, and the usual process is to pick one of these Bragg peaks, say this one, and pump it and watch it and hopefully see it go to zero. And that will tell you about the phase transition. Okay, so the main goal of my talk is to answer this question. Is monitoring these Bragg peaks, which has been done actually for quite a long time now, telling us everything that we need to know about the dynamics of the system. So let's just, before we go on to what happens in VO2, I'll give a case for a magnetic system. So magnetic memories rely on storing information on whether or not the system is in a spin up or a spin down state to record the state of the data bit. Okay, and so what we should remember though is in the magnetic system, the spin up state is not made from a single spin, but is actually made from many, many spins, which have a net alignment along the up direction. And the same goes for obviously the downspin state, that the many, many spins are rotated around to the down state. And how do we get from the up state to the down state? Well, the spin can't go to zero, an individual spin can't go to zero, but the MZ component can go to zero. And so one way would be that we rotate it, say, all along the x-axis. This would give an MZ equal to zero. And then we keep on rotating along the x-axis. So we take our spin up, we rotate it 90 degrees and carry on rotating it back to the spin down direction. And that process is quite similar to the process I sort of described with the phonons in vanadium dioxide. And it's quite a coherent process. But is that what actually happens inside data hard drives? And the answer is no. So if we take the most recent magnetic recording technology, which is heat-assisted magnetic recording, the system starts off in the order state, but then it uses a laser to rapidly heat the system above TC. And when this occurs, the individual spins, they lose their preferential order and they randomize. Okay, and now we're in a state where MZ is equal to zero, but it's very different from the rotated state I described before. In order to induce the new state, you have to apply a magnetic field to the system, and this causes a preference to be orientated in the spin down configuration in this case, and allow the system to cool. And once the system has cooled down, you can take the magnetic field off and it will be trapped back in the spin down state. Okay, so what is interesting is we have two routes suggested here, and obviously there's a continuum between both extremes in which the system passes through a state where MZ is equal to zero, but there's not a unique MZ is equal to zero state. So that macro state can have many microstates. And the two cases I've shown here are a system in which goes via a high entropy state to generate the inverted state, or there's a coherent low entropy state in which there's a uniform rotation of the spin system. Now, the interesting thing is that Bragg scattering, well, it can't normally measure magnetic degrees of freedom, but in general, Bragg scattering could not separate these cases because Bragg scattering can only measure the average component. And both cases have MZ on average equal to zero. So the rotated intermediate state or the disordered intermediate state. So we need to do something else in order to probe this and just look at Bragg scattering. And just to sort of emphasize before I talk about how we're going to do that, In the phonon situation here, I just show the two cases of the high temperature phase of vanadium dioxide, or possible high temperature phase. And one is the low temperature, low entropy high symmetry state, in which I started from at the beginning, where I drew all the atoms in the high symmetry position. And on the right-hand side, I show the disordered case, where there's still no net delta, and there's no net distortion in the system. It's hard to show that with only 4 atoms. So you have to imagine a larger system in which there is 0 average displacement from the high symmetry place. But now you can represent the displacements by a non-zero q squared. So the low entropy state has a finite q squared. It has 0 q squared. So not only is the average position 0, but the displacements are 0. And one thing that's worth thinking about or important is that this is not a static disorder. This is a dynamic disorder. So at any point in time you look at the high entropy state, it will be different. The atoms will have moved because they have some thermal energy, but still on average, the Q is equal to 0, but Q squared is finite. Okay, and this, my final thing before I tell you how we're going to measure this, is the implications of a coherent transition and a disordered transition on the evolution of the system. We saw about, I think both talks maybe, but Andrea mentioned about pushing the system over the barrier into a new state. And if we have a coherent evolution, that's quite straightforward to imagine that we start in a system with a dimerized state, we initiate some pulse, some force, which causes the dimers to break. They move along the potential energy surface and they get to the state where there's no net distortion in the system, but they might still have some momentum in them, which would allow the system to go over the barrier into the other potential. And so then we would switch from one phase, one twin, as we would call it, to the other twin in a coherent fashion. That cannot happen in the disordered evolution. So in the disordered evolution, the forces are can no longer be uniform on each atom. So each atom cannot just move along the high symmetry direction, but it has to move in a random way. We again reach at a certain time, we'll again reach the state where there's 0 net distortion in the system, but there is now a finite buildup of disorder measured through the mean squared displacements around that position. And if we let this system carry on evolving, it may overshoot to the other side of the potential, but it's not going to be trapped. And the disorder will potentially carry on in growing. And what's really happening here is, I've tried to draw that with the size of the balls, is that the system is no longer really describable by this simple potential energy surface, okay? So on the coherent evolution, the system is described by a single phonon at 1 k vector, which is essentially what I'm plotting here, would be the free energy on the left-hand side. These blue lines would be as a function of a phonon at one specific k vector. Now, as we go into the disordered case, 1 k vector is no longer enough. I need many types of distortion to disorder the system. And so the system in one particular k vector is represented by a smaller and smaller piece of the pie, I guess. And so this will eventually disappear completely, and the system will be spread out through more k space. Okay, so how do we measure that? There's an excellent review article, which is available in Nature, written from the point of view of neutron scattering, but it also applies to X-ray scattering, and that's the crystallography of correlated disorder. Really recommend everyone to read it. And the point I would like to make is that disorder in general is hard to see because in Bragg scattering, you can have these 3 cases where there's complete order, where this is water, and when the oxygen and 2 hydrogens are forming a completely periodic structure and giving rise to the Bragg peaks. And now we have a case in B where the oxygens are allowed to rotate, but the motion is not completely disordered. So now oxygens prefer to form in certain preferred directions, but not necessarily with any long range order. And what you see is that, well, it's not so clear on this plot, but the Bragg scattering intensity is hardly affected by this type of correlated disorder. But in between the Bragg peaks, and this is on a log scale, you can see some diffuse scattering, and this is very sensitive. Okay, so this shows you that there is some strong correlation between neighboring hydrogen ions atoms in this crystalline form of water. And then obviously you can go to the completely disordered water over here where the correlations are lost. And now you see a very isotropic type of diffuse scattering. So we have lots of information available in the diffuse scattering, which is not present in the Bragg scattering. So we need to look at this diffuse scattering because this tells us how the disordering is going in vanadium dioxide. And so here I just show that you can do this statically in vanadium dioxide. And what you find in the low temperature phase is the system is very harmonic, which means that there's a very, much like case A, where there's little disorder in the system, entirely ordered. And when you go into the metallic phase, the system is behaving more like this correlated disorder. And that's because the metallic phase of VO2, it likes to form dimers. It prefers to fluctuate along those directions than others. And so there are two key things we want to look for. We want to look for the loss of the Bragg peak, which is this guy. You see this guy here is a monoclinic Bragg peak, which only appears in the low temperature phase. It's not there in the high temperature phase. There are some Bragg peaks which are present in both phases. So you see those. And then these are the stripes of diffuse scattering, which we want to look for in the transient response. Okay. So one of the challenges for this is that the reason why this has not been done before is that diffuse scattering is weak, and we need to go to an X-ray free electron laser in order to get X-rays bright enough to be able to see it. So we went to LCLS in Japan. And just to reiterate what we want to do is what we expect to see is that so we went to LCLS in the USA, in Stanford, and we look for certain peaks that are going to go down in intensity, certain peaks are going to go up in intensity, and whether or not this is a displacive transition or a order-disorder transition will be whether or not the diffuse scattering goes up or stays the same. Okay. So that was that slide. Okay, the experiment is actually very simple. We just put the sample in a grazing geometry. We come in with the laser and X-rays, and this is how it looks on the detector. This is in LCLS now. We have the CS pad, which gives this unique pattern to the image. And I've highlighted here 3 monoclinic peaks, and I've also highlighted which disappear in the high temperature phase. And I've also highlighted the diffuse spectrum that were diffuse regions of the system, which we're going to look at here. So we expect these guys to disappear, and we expect this intensity to appear. And the question is, how and when does this occur? So, okay, I'll show you the summary of the left and the right. And we're going to watch a video now. You have to pay attention because it's very fast. You see, okay, on the top left is time. This is in picoseconds. I'll show it again. We see that now, okay, so I stopped it at 100 femtoseconds, the video, and you can see already there's a very strong diffuse scattering in the positions that we were expecting it to appear. Okay, and I'll just see, then it's stable for a long time afterwards, actually continues to be stable for many hundreds of picoseconds. Okay, so what are the timescales involved? Well, we can take frames from this movie and plot the diffuse scattering, which is a measure of the disorder in the system, which are the purple dots here compared to the Bragg peaks. VO2 is a little bit more complicated than the simple picture, so all the peaks labeled red should go to 0 when they're photoexcited, and they nearly all do. And then the peaks labeled yellow are present in the rutile phase, so they should go up in principle, but because of the structure, some of them actually do go down as well. I mean, they should go down. And the lines are results of molecular dynamics simulations for the phase transition, which have no free parameters. And with the exception of the solid line for the diffuse scattering, which is actually literally Q squared and not the sort of total diffuse scattering, but they're very similar to each other. And the important point here is that we find that all Bragg peaks and diffuse scattering changes happen at the same time. We see that the system has the same threshold as observed in optical experiments. And this tells us that the system is disordering. And so from the MD, we can see what's visualize sort of what's going on here. We plot I'm plotting now bond length instead of the atomic position, but we have a short and a long bond due to the dimerization. And we see that this nearly instantaneously collapses onto a single bond. Here are the distributions. So we have an initial thermal distribution of the bonds to start with, and they very quickly collapse onto a single distribution. And we could think of this as a disordering or a high entropy process, because after a few hundred femtoseconds, we can no longer decide if an atom started off in a short or a long bond. So that this system has lost all sense of order. Okay, so that puts VO2, it brings me to my conclusions. I think I've gone a little bit fast actually. Brings me to conclusions, but it puts, it shows very clearly, I think, that vanadium dioxide is driven actually by phonon disorder in the system. And this is in a way quite challenging because this suggests that this disordering in the phonon means that we can't reverse this phase. So what would be nice in vanadium dioxide in many systems is not only the ability to go from one phase to another phase, but be able to bring it back. And reversing a disordering type of process is much harder than reversing a nice coherent style process. What we don't know at the moment is this transition unique to vanadium dioxide? Or so is vanadium dioxide unique amongst the phase transitions? It's the only one which has been measured with diffuse scattering so far, so we don't know how this plays, or is it unique to photoexcitation? It could also be that the photoexcited carriers are key in the disordering processes, and processes like Andrea mentioned, which are using resonant lattice excitation, do not suffer this type of pathway. So that's one thing that still needs to be investigated. But another interesting possibility is that can we use this disorder as a unique knob to control material properties? If you think many calculations are done in quantum materials on quite small systems because they're difficult to perform the calculations. Disorder requires large unit cells, but many materials like glasses have many advantageous properties because of disorder. And so they have benefits from being disorder rather than in order state. And maybe these transient phases are resulting from disorder that we can generate in a new way in the ultrafast regime. And so I think the thing that we sort of know for sure is that we do, well, I think we know for sure is that we don't know how electrons and phonons really couple in a non-equilibrium regime, because before we started this work, if you had asked people how quickly does the energy transfer from the electron to the lattice, they would say of order a typical phonon period. And I didn't really go into the time constants here, but we find that this disordering occurs very, very fast, much faster than the phonons in the system, particularly transferring energy into transverse acoustic phonons on a few hundred or sub-100 femtosecond timescale, which is much faster than their intrinsic vibrational timescale. So I think this shows that when we go through a phase transition, we really do not understand how the energy is coupled in the system, and that's something that we should look for. So in the last few minutes or seconds, I would like to thank my collaborators on this. I've put the four actually key collaborators: Luciana Vidas, who's my PhD student at ICFO, who did the bulk of this work; Mariano Trigo at the Pulse Institute in Stanford, who's a real expert in time-resolved diffuse scattering; and Olivia Delaire and Yan Shang, who are really the I guess experts in static diffuse scattering, and Shang in particular did all the calculations for the phase transition, and they're at Duke University. But there were actually many more people involved, and I refer you to our publications to get the full acknowledgements list. And finally, I'm just going to do a bit of promotion. We have two other presentations from our group today. So on the question of whether or not VO2 is unique is, I think, one that we're trying to look for now, and we've decided to look in the manganites in LSMO. And Daniel Perez has a really nice poster on our new setup to try and have a better approach from the optics to try and make it more competitive with X-rays. And so he's built an ultrafast birefringence setup to measure the order parameter of orbital ordering. And there we see, I would say, things that are very consistent with vanadium dioxide. And then if you were awake and watching, you would have seen on my slide the VO2 has multiple phases and it's a first order phase transition. And this often leads to phase separation. And Alan Johnson will be giving a talk later in the day on how we can use coherent diffraction to image and also go beyond imaging to do nanoscale X-ray spectroscopy on these phases in vanadium dioxide. So with that, I'd like to thank you for your attention and if you are interested in a PhD or postdoc, get in contact.
Okay, Simon, thank you very much for this very interesting talk and also for finishing nicely on time. So this means we can now start with the questions. So again, not too much activity on the chat yet. So maybe I can ask a question then. So you were saying it's faster, this transition, than you would expect, right?
Mm-hmm.
Yet
yeah.
the MD simulations completely match.
That's true. Yeah.
So is there anything you put in the simulations that was still unknown, or?
Yeah, so that's a good point. And I think when I say expect, I think it's based on these expect based on sort of simple premises, whereas the MD is the full evolving under the full force field of the phase transition. So normally, I think one sort of expects the timescale for electron-phonon coupling to be related to the phonon period of interest. That's just I think a general concept which is coming from I guess a more low density excitation sort of scenario. Once we're in the very highly excited state, that breaks down, not necessarily for anything complicated or any complicated reason, because it's captured by the molecular dynamics without a problem. But it just shows you that these sort of maybe naive or simple pictures don't apply once you get to the high fluence limit. Not necessarily that there's anything fancy going on, I would say.
Okay, so these are just classical MDs with a standard potential, or?
This is, yeah, so it's done with DFT plus U, which is not ideal for the vanadium dioxide, but it's, you really don't want to use plus U if you can, but it's too hard not to. So I said there's no free parameter. There's a free parameter in tuning the U to get the equilibrium parameters, but there's no time-dependent additional parameter, or the electronic temperature, which we excite the system to. But
okay,
that's the other one.
Okay, thanks. Any more questions? There is still some time, so don't be shy. Just write something in the chat.
So I would say I can add one thing. The thing that is clear in the MD, but is not completely clear, at least for me, is how we generate this range of forces. So the coherent phonon is fine to image because you know that the light has no momentum, and so that's a Q is equal to 0 sort of force, and the light there's no Q is equal to 0, so that conserves momentum. But generating a random force, maybe this also answers a bit more the question, is harder because the light has to act on each phonon differently, or each atom differently, and it can't do that with its low momentum. And so there is this step which is going through the excited state, which allows this randomization of the force, which is maybe not being discussed too much in the literature so far.
Okay. I see there's a question, so let me unmute. Yes, Celine, please.
Hi, Simon. Yeah, I was wondering whether we can still say something about the electronic structure. So
yeah.
Of course, when we do scattering, we look at the lattice, but what do you expect the gap to do meanwhile?
The gap, well, yeah, so I mean, we calculate the gap also in this. I don't think we plotted it in the paper, unfortunately. Yeah, so I guess that the gap closes sort of also instantaneously with these, in this simulation along with the lattice. So it's also going very quickly, I guess. Yeah.
And do you expect the time of both the disorder taking place and probably the gap closing being fluence dependent?
Well, so there's I didn't mention this. So there is a so one of the ways in there is a discontinuity. Although the agreement is very good in the diffuse scattering in the calculation at room temperature, what we tried to do is cool the system down, and in the molecular dynamics, what that does is it reduces the initial disorder in the lattice. And so that suggests the transition is slightly long, or at least not the transition is longer, but the coherence in the lattice persists a little bit. But when we did the experiment, which is we're in the process of writing that up, that did not occur. So at low temperature, we did see exactly the same timescale as a high temperature. So this is not necessarily directly answering your question, but that shows that there is something that we're missing in the MD, which is how to sort of completely understand this scrambling. Whether or not this how this affects the gap is quite difficult, because I don't think I know my electronic structure and disordered systems well enough to be able to make a good estimate of how the gap would be quite a local thing on a very short time scale, I would say. So whether or not how you see that in a probe of long range electronic order is harder for me to make a prediction. So I would say that locally the gap would be breaking very quickly. I don't know how quickly you need, or how much you need to make before you close the gap, but I would guess that the gap goes very quickly with the disorder. Hopefully that answers the question. And I don't know now if I cannot hear anybody because I'm not meant to, or. So did we lose the host?
Yeah.
Yeah. Okay. Well, at least that's the difficulty in the without video. Oh, there we are. Yeah.
Sorry. Yeah, that's because I passed the host to Agostinho, who will chair the rest of this session. So because there are no more questions, I think, in the chat. So I suggest we thank Simon again for this very nice talk, and we move on with this session. So as I said, from now on, it will be Agostinho chairing this session.
Thank you very much, class. Good morning, everybody. Let's move on to the second part of the morning session of this mini colloquium. I know that we have to wait, let's say, 1 minute in order to wait for people that can attend the regular talks. So in the next section, we will hear 3 regular talks given by 3 different researchers. I can introduce now the first one, Yizheng Fieng from Max Planck Institute, Hamburg, Germany. Are you here? Yes?
Yeah, I'm here.
Okay.
Let me share my screen.
You can prepare, yes, you can share your.
Okay,
so we will proceed as class. When it's missing 5 minutes, or when 5 minutes left, I switch on my camera. Okay, it's for you the signal that 5 minutes is left for the end of your talk. Then we have 5 minutes for questions. Okay. What time is it? We can start now. Please.
Okay. Hello, everyone. My name is Yihun Jiang. Currently, I'm an instrument scientist in FXE group in the European sphere. So I'd like to thank the organizer for giving me this opportunity to present my work. And this work was performed in my previous research group before I joined the European sphere last year. So this work is also part of collaboration between Max Planck Institute and the University of Toronto in Canada. So the title is Direct Observation of Nuclear Reorganization Driven by Ultrafast Spin Transitions. So once we have the spin crossover, it will cause a lot of electronic state dynamics, and we are looking the nuclear reorganization, which is matching this electronic state dynamics. So in the beginning, let me introduce spin crossover. In spin crossover is a conversion from low spin ground state to high spin excited state due to temperature change or light absorption. Spin crossover has been studied for its potential applications in optical memory and photo switchboard devices. Among spin crossover compounds are ion 2 metal with an ion 6 environment is the largest. After ion 2 compounds absorb the light, the ground state changed to the high spin excited state by two paired electrons entering the anti-bonding orbitals as unpaired electrons. Therefore, the ion-nitrogen coordination bonds are getting weaker, and we see around 0.2 angstrom ion-nitrogen bond elongation. Also, let me introduce the methods I use to study this structure change. It's ultra-fast electron diffraction. So the setup I used is a 95 keV DCI hybrid electron gun. So we use 95 keV DC high voltage to accelerate the electrons, and we have RF cavity to recompress the electron pulse duration at the sample position. So really, single pulse, we have 10 to 4 or 10 to 5 electrons, giving the factor of 10 to 5 times higher scattering factor. So this brightness is similar to free electron laser, and the pulse duration is around 275 femtosecond. So in my talk, I'd like to discuss two UED studies of spin crossover. The first one is UED study on ion PM-AZA, and the second one is the UED study on ion transbipolarity. So let me start with the ion PM-AZA. So this is the diffraction pattern of the ion PM-AZA. We can see the diffraction quality is very good. We can see many peaks and even very high orders. And this is very useful for the later data analysis. And the picture B is the signal we measured when we change the temperature. So this is the signal from the thermal-induced spin crossover. Picture C is the signal introduced by photoexcitation measured after 10 picosecond time delay. The last one is the difference between low T and high T data. So we use it to simulate what is the signal we're supposed to see. And we can see B, C, D all can match very well. That means we did pump the sample to the high spin state, and the structure is very similar to the thermal-induced high spin structure. And for this one, we can see the short time relative change in the intensity of select bright spots in the first 20 picosecond, and this is the later is for the first 1000 picosecond. We can see there's only one step, and the time constant around 2.3 picosecond, and we reached the high spin structure already. And for the long-term one, we start to see a lot of phonous oscillation, but this is not really related to spin crossover dynamics. Okay, so we have the diffraction pattern. We have the change of the diffraction pattern intensity, but how we get a lot of structure information from that? Because we only have one orientation. So literally we only study one crystal plane. So our idea is to use struct vector and Pearson correlation to do principal component data analysis to know the overall structure information and obtain the molecule movie. So in the beginning, we need to calculate the excitation fraction, which is very important for the further data analysis. And also we need to index the diffraction pattern. And first of all, we may do some model compression. For example, for this ion PM-AZA, I assume if I only see ion-nitrogen bond elongation, what kind of the diffraction pattern change I should see? And also what may happen if ion-nitrogen bond elongation is coupled to the overall ligand motion? What kind of signal I should expect? And then I compare these two models to the experimentally observed diffraction pattern changes, and we just see which direction might be good. But in this work and in the later work, we do far beyond this step. So what we do is we set a few key structure dynamics groups because we cannot allow around 100 atoms to move freely and get the structure. So we set 3 key dynamics groups based on the knowledge of chemistry and the knowledge of this sample. For example, for this sample, the first component is iron-nitrogen bond elongation. The second one is the ligand rotation. And the last one is the unicell expansion. Then we allow them to move towards the high-spin structure or can even go back. So we allow them to move. Then we have a lot of different combinations. Then for every different time delay, we have a relative change of the diffraction pattern. We compare the structure we simulate and to the experimental observed changes of the Bragg peak. And then we can know what is the best fit of the structure at this time delay. For example, for this one, we can see those 3 components are coupled toward the high spin structure, but in the end, they can never really reach 111 because this 111 structure is the thermal induced high spin structure. But we pump the sample at a low temperature. So that means the unit cell is relatively small. So that means this model must reorganize itself in a relatively small unit cell. So that's the structure we can get for the photo-induced high-spin PMAZA. Also, it's important to notice the time constant we obtained matches with the time scale of intramolecular vibrational energy redistribution obtained by transition absorption. And this IVR of hot excited high spin molecules and energy transfer from iron to nitrogen to the rearrangement of the ligand and the unit cell. The slow time constant can be explained by the 2 picosecond bond distribution narrowing during the IVR because our electron diffraction is probing the ensemble average of iron-nitrogen bond lengths. So for this part, I will further compare it with the next work. So in the end, we see 1-step process and no further intermediate state. Okay, then I will talk about the UED study on ion transport purity. Ion transport purity is a textbook for ion to spin crossover dynamics. And this work was published a couple months ago. So it is a very standard sample to study spin crossover. So it has been studied by transition absorption, X-ray absorption near edge, and also X-ray emission. And even in my current group, we use its ultrafast signal to find time zero. So it's very established dynamics. But still, electronic state change has been studied very well, but the structure information is still not very clear. For example, by X-ray absorption near edge, they can kind of like study ion-nitrogen distance because X-ray absorption near edge is sensitive to the target atom to its closest atom's distance. So they can see oscillation of the ion-nitrogen bond distribution, and it's narrowing down in the high-spin energy surface. But what is ligand's role and what is ligand response to this ion-nitrogen bond elongation is still unknown. So in order to study it, we must use diffraction. So we can either use X-ray diffraction or electron diffraction, and we use electron diffraction to study it in this work. So it's also important to mention it's a very low frequency excitation, single photon absorption structure study because electron diffraction is very, very sensitive to the sample damage. So even a little bit of damage, we can notice easily. So we use very low frequency. We only pump 10% of the overall molecule, so 10% of excitation fraction. And it's also the first time we can really measure the photo-induced high-spin structure with atomic spatial resolution. Because for this ion transport purity, there's no thermal spin crossover. So people can only do some basic simulation to guess what is the high-spin structure. But by this work, we can actually measure it and tell people what is every atom's position is. So later we also discuss the structure effects by comparing two UED results. So we can see this one is similar to what I showed for the ion PM-AZA. So this is the diffraction pattern for ion transparity. And this is the signal after 5 picosecond time delay. This is the signal after 100 picosecond time delay. This one is simulated stroke factor change during the spin crossover. So because there's no high spin structure for a single crystal, so I adopt the simulation for the solvent to the crystal, and it gives us a kind of signal which is similar to what we observed in our UED work, but the detail is not very close. They indicate this structure is not exactly the same. So it's also important to show the short time relative change in the intensity of selected bright peaks. So we use the global fitting of the bright spots to show bi-exponential fit and the mono-exponential fit of the relative intensity changes. And we can see the bi-exponential fits with 450 fast components and 2.4 picosecond slow components and can fit with our time trace very well. So we have two parts. One is 450 and the second part is 2.4 picosecond. And we assigned the first ultra fast part is ion nitrogen bound elongation coupled with the ligand motion. And the 2.4 picosecond part is the molecule reorganization relaxed down to the bottom of the high spin state. So in order to get the molecule movie, so for this work, I set 4 key structure dynamics group. One is ion nitrogen bound elongation only, one is ion ligand elongation, and then this is nitrogen ion nitrogen angle rotation, and also the ligand rotation. So when we do the principal component analysis, I can know the contribution of those structural components for every time delay. It's important to notice for local ion nitrogen bound elongation and the structure change, they all can reach almost 100% like people suggest in the solution. However, for the ligand, they never can reach that much compared to what people suggest. I think it's still because of the related the unit cell and also the chemical pressure from the neighboring unit cells. And also important to notice for the local structure change, they all can finish a lot in the first component, and they also finish quickly. However, for the ligand part, they only change half in the first component, and most of them happened in the later part. So it's easy to imagine if this molecule has an even longer ligand with less symmetry, like what I showed PM-AZA, then this part will be even smaller and even not obvious. It's also the way why we don't see ultra fast part in the PM-AZA work. I also have a video to show. So 4 key modes. So first is ion bound elongation and the rotation and ion ligand rotation. And this is the events. So maybe too fast, not clear. So let's repeat again. Blue is low spin, red is high spin. So it's important to notice. So all the video I showed is not a cartoon. It is, we really know every atomic position at a different time delay. So it's a real, kind of like very close to a real molecule movie. Okay, so how we understand the difference between PM-AZA and ion transparity? For BPY, the photoexcitation is followed by spin transition, and the vibrationally hot high spin state has a narrow ion nitrogen bond distribution, and it vibrationally cools inside the high spin state within 2.4 picosecond. And for AZA, the ligand structure rearrangement is distributed during IVR, resulting in a border distribution of the structures and narrows over 2.3 picosecond. And by this comparison, we show the role of the ligand by total number of low frequency mode, symmetry of the ligand, and the number of degrees of freedom. And the difference between these two molecules is the result of the different high spin energy surface, different starting points, and the degree of coupling for the relaxation path. So I'd like to summarize. So in this ion transparity work, we show a two-step change. The fast one is 450, the slow one is 2.4, and the fast one can be assigned to be combination of ionization bound elongation and the ligand motion, and use the principal component analyze. We uncover four key structure dynamics modes to capture the molecular reorganization. Okay, in the end, I'd like to thank my group in Max Planck, Miller Group, and also European Exfield, and collaborators, Ricky, Eric, and Samurai. Thank you, everyone.
Thank you very much. We have 4 minutes for questions. Please ask questions. May I start? I would like to ask you, what is the main mechanism associated with the iron-nitrogen stretching bond mode in this spin dynamics?
Can you repeat the question again?
Yes, you showed that there is a structural and magnetic coupling in your system, and at the end, if I understood well, you said that iron nitrogen stretching bond mode can be, let's say, the main mode to underline the spin mechanism. Could you explain better this mechanism?
So, so the spin crossover, one of the direct results, structure result, is the iron nitrogen bond elongation. Mm-hmm. And the reason is, like I showed, two paired electrons in the low spin, one to the anti-bonding orbitals is unpaired electrons. So it's breaking the pi back bonding from the nitrogen. So in the end, the coordination bond is weaker, and then it gives us the iron nitrogen bond elongation. And this is original, like the reason why we even see a structure change in joint spin crossover. And for many works, it has been showed is around 0.2 angstrom iron nitrogen bond elongation.
Did you try to study this spin crossover using other ligands?
Yeah, I for example, the first one I use is ion PMAZA. So the ligand is like that, and later is ion transparity. So the symmetry is different, and the ligand is also different, and that's the reason why we see the different behavior when we pump the sample.
In your molecule, you have only one magnetic cation. Did you try to couple using different ligands with different cations, magnetic cations?
Yeah, that's something I will do in the future. But in the beginning, I would like to make everything as simple as possible. In particularly for the ion transparity, it has been very well studied. That I can get a lot of information from other works. So in my view, UED can only see one aspect of the overall dynamics, and it's complementary to what people did by transition absorption or X-ray absorption, age, and X-ray emission. So overall, combining all the information, we can get a bigger picture and even clearer picture of the overall dynamics.
Okay, thank you very much. More questions? We have time for a little question. If not, I would like to thank Ji-Fiang for his nice talk. And we move on to the other regular talk. Min-Jae Kim.
Yes.
Will you share your presentation?
Yes.
Kim comes from Max Planck Institute from Stuttgart. Okay. So.
Can you see it?
Yes.
Yeah.
Is everything okay? You can start.
Yeah, thank you for the nice introduction. And hello, everyone. My name is Minjae Kim, and I'm from Stefan Kaiser's group of Max Planck Institute for Solid State Research. And I'm going to talk about today collective excitations of exciton insulator tantalum nickel selenide. And this work is collaborated with Andrea Danoy-Schelle's group from UBC and Hidenori Takagi's group from MPI and Tokyo University. And firstly, I will briefly introduce about exciton insulator. Okay. So excitons excitons are bosons and can condensate, and theoretically we can expect this phase diagram. And when the semiconductor has very small band gap energy, even smaller than the excitonic binding energy, then it starts to condensate. It shows condensate. Oh, sorry. Condensate, and with a gap is opened. And this happens also in the semi-metal side. And we are going to study today about tantalum nickel selenide, which is a zero gap semiconductor system and which has a TC transition temperature at 328 Kelvin. This sample has crystallized in one-dimensional, quasi-one-dimensional chain structure, and electrons hops from nickel to tantalum, and it forms the charge transfer exciton. And the system has a direct band gap, and which means we can avoid charge density wave contribution when we study about this insulating transition study. So experimentally, we can see the characteristic band flattening because of the condensation, as you can see in RPS measurement. And in transport measurement also shows your TC is changed by the statement of the doping. So you can see this characteristic phase diagram of exciton insulator, but we are still missing the coherent dynamics of collective mode of the exciton insulating state. So we started with a optical pump probe measurement to see the intrinsic coherent dynamics of the excitons. So we pumped at the to the continuum, which means the far above the than the energy band gap of the system, and then this is the result. Yeah, in principle, we need 10 femtosecond pulse length of the pulse length for the measurement, because our system has the band gap of 160 millielectron volt. So this is the result. At the excitation of the early time excitation, you can see this coherent oscillatory behavior, and the F50 of this shows the collective modes, which is mainly three modes. And first two modes we call exciton bidding mode, because those energies of the mode corresponds to the different energy of the exciton, each exciton energy levels. And the remain mode we call exciton, so remain mode is at 38 terahertz, and this energy is corresponds to the extonic binding energy. So therefore, we can call this is Higgs equivalent mode. But this modes and this external levels intrinsic extonic bidding energy shows us there is this system is like a Rydberg series, and this means it indicates vanille type, 3D vanille type of exciton state. But we know in structurally, there is a charge transfer exciton in our tantalum nickel selenide. So what makes our excitonic coherence length getting longer? So it's already discussed in static optical measurement. There, we suspect there is pleronic complexes in the system. So it's worth to try to see the phonodynamics in the system to see the relation with this exciton condensation and lattice. So we pumped with the longer time scale pulse to see the coherent phonon mode. And you can see this excitation and the relaxation dynamics on top of it, this collective current phonon modes. And the longer time scale, we clean out already known the phonon modes. So the interesting part of here is, so the so different from the other phonon modes, this first 1/3 phonon mode shows as temperature changes, it shows this amplitude mode-like behavior. So from this, we suspect this 1/3 mode indicates there is a coupling of external condensation with this phonon mode. So this is first observation of the coherent external condensate. So the question is, can we see this coupled external condensation coupled phonon mode in also the measurement of band gap dynamics directly? So we can measure time resolved RPS to probe transient band structure. There are 2 papers about it already. So first paper is from Berlin, and it argued about back gap enhancement. When we pump hard enough, then this valence band is valence band start to getting lower. That means the gap is opened more. But oppositely, so the other paper from Tokyo University argue about when we pump hard enough, then we can see the spectral weight push into the gap. So verify this, and we want to see the gap dynamics of our measurement. So we reproduce this measurement. So this is our results. You can see this video with after the pump. You can see this spectral weight changes. And following the previous papers of procedure, so we integrated it at the center of the band, and we got this energy distribution curve, and you can see this clean different curve line shape before the pump and after the pump. So firstly, we want to verify the gap enhancement. So we took this spectrum with only the top of this band, and we fit with single Gaussian function, and so we trace all time dynamics, and this Gaussian, the center of the single Gaussian function shows the blue shift. That means the gap enhancement as we saw in previous work, but at all the time delay, you can see this also at the same time spectral weight, which is being pushed into the gap. So, and moreover, we found out in our measurement, with our resolution of the measurement, it shows this first band is not fitted with only one single peak, but we need at least 2 peaks. So the dynamics of the peak to peaks are, both peaks are broadened after the pump, and the intensity of those peaks are different. So this red peak is shifted as strongly suppressed after the pump. So that means the center of this first band can be shifted from red peak to blue peak after the pump. So yeah, so we in our measurement we are in the more same line of the interpretation of Tokyo University's paper, because we have always this spectral weight pushing into the gap. So now we are going to see the dynamics of this missing spectral weight. So we integrated only the top of the band. So this integrated intensity shows this on top of this incoherent excitation and then relaxation. You can see this small oscillatory behavior, and we clean out with the fitting, and then we can see this clean oscillations, and for different pump influences, all the measurements shows this oscillator behavior, and the so we can see this clean oscillator behavior in many twice of the fluence as optical pumping. And the FFT of this FFT of this oscillations gives mainly two modes. So first mode is at 1 terahertz, which we already saw in the optical pump probe measurement, and with this mode in the function of fluence, it starts increasing, but it's depleting because it shows, yeah, that is similar to the optical pump probe measurement because of this 1 terahertz phonon mode is coupled to the condensation. So this is shows similar behavior, but we found one another interesting mode which sits on the 0.5 terahertz and which increases, but it's saturated. And this we can see in the coherent phonon dynamics in previous work also. It's similarly, so it's similar to this current phonon dynamics. So we know there is no phonon mode at this range, and we can say this is electronic coherent mode, but it behaves like a phonon saturation. So we from this we suggest this is a Polaronic mode, which is the lattice contribution to this mode. But we know already from the line shape of our band, so we can assume there is a strong coupling to the phonon, because when we compare to the cuprates, so it shows the anomalously broad because of they suggest there is a polarance in the system with strong electron phonon coupling. So as it's already suggested in the static optical measurement, there we suspect there is Polaronic complexes, and this Polaronic mode is from this Polaronic complexes. So can you see this Polaronic mode in not only the RPIS, this gap dynamics, but also in optical pump probe dynamics? Because when we see this coherent phonon modes, we clean out with only longer time delay for cleaning out, but and at all total time delay, so whole time delay, that we found out there is a oscillatory behavior in at the early time. So FFT of this total dynamics, then we could find there is this Polaronic mode at this similar energy range as we saw in RPIS measurement. So the possible interpretation of this Polaronic mode is the coherent current, because of the line shape of this oscillation is reminiscent to the broadband terahertz pulse. So if this is coherent current, we should see this oscillation in the terahertz range. So we tried to measure optical pump terahertz probe, and this EOS sampling field is from the sample, the reflected from the sample, and the dynamics of this position shows after the pump, optical pump, it shows this single cycle like oscillatory behavior, even below the TC and then above the TC. So we checked there is a coherent current, and the possible interpretation of this is if there is intrinsic Polaronic complexes in the system, when you pump onto the system, this excitons can be temporarily broken, and it flows, but it flows slowly because of the lattice contribution. So we can generate driven Polaronic current. So I'm going to summarize my talk. I've shown you with very short laser pulse to see this intrinsic external current dynamics and Higgs equivalent mode. And with longer timescale pulse, we saw the phonon-coupled external condensation. And finally, we saw the dynamics of the gap. And from the collective excitations of the gap dynamics shows not only the phonon-coupled external condensation, so one turns phonon mode, phonon mode, but also we could see this driven polaronic current, which is also observed in terahertz range. So this is all of my talk, and thank you for the attention.
Thank you very much. Thank you for your nice talk. We have time for questions, please. Please. There is one. Please, then one. Yes.
Do you hear me?
Yes, yes.
Okay, thank you. So Minjay, I have short question. You mentioned that this intrinsic dynamics is equivalent to Higgs mode. Could you explain a bit more why it's Higgs mode?
More about it, or?
Or I mean, why you see this amplitude oscillation, or so why it's equivalent to Higgs mode?
Oh, because yeah, because this external condensation. So we excite. We could see this external condensation and the Higgs mode dynamic. So equivalent Higgs equivalent mode dynamics means equal to the gap dynamics of the external insulator.
Okay. More questions? More questions?
Yes, now I'm into. Thank you. But from the experiment,
it's not unclear, or
from the experiment, do you have evidence for this, or it's more like this is known from other experiment already? You can. So, do you have evidence from your experiment that this is Higgs mode?
Higgs mode?
Yes, I mean not directly from your measurement. Could you say it's Higgs mode or not, or you have to compare to other experiment to claim this?
As I know, there's only this amplitude mode measurement of this system is kind of first probe in this second work.
Mm-hmm. Mm-hmm. So it's optical palm optical probe. You see this one.
Yes.
Mm-hmm. Okay, thank you.
We have another question from Simon Wall.
I think it's because I'm co-host and I couldn't raise the hand in the co-host. But do I have time to ask a question?
Yes.
Yeah. So very nice talk. I guess the question I have is on the polaronic part of the talk. I struggle to understand this part really because I don't. How does the optical view really see the polaron? Is a very local. The picture is a very localized phenomena. So I imagine there's not much coherence between them, and yet to get this signal, I imagine you need quite a long range sort of coherence between the polarons. Is it really like the picture you drew, where it's just a few sites, or is it actually more of a long range thing? That's sort of part one. And part two would be, can you exclude things like, say, just surface terahertz emission or something like that from this terahertz field that you see?
Yes, actually, I've drawn this No, actually, this polaronic complexes is suggested in static optical measurements. Firstly, so this is static optical measurement, and then this it suggests this excitonic levels. So excitonic energy levels is not in the below of the continuum, so in the gap, but it lifted up to the continuum. That means, so they suggested there is a strong phonon coupling to the excitonic state. Firstly, they suggested, and why we suspect this is the polaronic current, because so in principle, this excitonic energy is very fast, and it should be really, it's like this mod insulator. It should be really, it oscillates very fast in few 50 femtosecond or something here. So compared to this, we cannot really directly compare to this paper, but in our measurements also so expect very fast oscillatory behavior, but it's getting picosecond coherent current, so we can suspect there is the effect of the polaronic effect. So what makes this so slow? And
so just out of curiosity, what is the pulse duration used on these measurements? It has nothing to do with rectification of the laser pulse itself, is what I guess. Because maybe it's in gallium arsenide, for example, you generate terahertz or surface currents that are, I guess, I'm wondering how it.
Current.
Yeah. I guess the question is, why is
like
there a polaronic current versus just another current or dipole current?
Yeah, maybe. Yeah, we've never thought about like surface current.
Mm-hmm.
Yeah.
Maybe if I can interrupt Simon briefly. So if you look at terahertz emission from this, if you take away the terahertz prompt, that was something we checked, you don't see any terahertz emission coming from the sample. So that would exclude any surface currents or something like this.
Mm-hmm.
It's really a pure transient response, so it's not a generation response.
Okay.
That was double checked.
Okay. We have to finish the discussion because we are a little bit delayed. Thank you very much again for the speaker, and then I will introduce Daria.
Hello.
Daria, okay. Could you share your presentation? Daria Gorelov comes from the University of Hamburg.
Hamburg.
Please. Please.
Yes, can you see my presentation? Yes. Great.
Yes, yes.
So yes, so my talk will be a bit different from the rest of the section. First of all, because this is a theoretical talk. And second, I'm not going to speak about any phonons or nuclear dynamics, but I'm going to speak about electron dynamics. Not just electron dynamics, but also about our suggestion how we can see this electron dynamics. How could we measure this electron dynamics? So here I'm going to show you the process that we consider or propose. It is called X-ray optical wave mixing. So the process that we consider is that we have an optical pulse which acts on a crystal, and this induces electron dynamics in this crystal. So the crystal is laser dressed, and at the same time, during this driving pulse drives dynamics in a crystal, we propose to image it with a probe pulse and X-ray probe pulse. So X-ray probe pulse will simultaneously shine on a crystal. So the idea behind that is that X-rays have a very short wavelength. That means that it gives access to atomic scale. So we want to see what happens to the electronic laser-dressed electronic system on an atomic scale. So how we theoretically describe this? So the interaction with an optical pulse. So here we consider bandgap crystals. In this case that I'm going to show you, it's the magnesium oxide. This is a crystal which is an insulator. It has very large bandgap, and an optical pulse drives dynamics with an optical pulse with photon energy below the bandgap, but of a very high intensity drives dynamics in magnesium oxide. So it is known that at such parameters, it induces high harmonic generation. That means that it interacts with magnesium oxides non-perturbatively. So in order to describe this, how it interacts non-perturbatively, we apply Flaquet formalism. So this is also an interesting formalism that because it not just describes with non-perturbative interaction, but also other very interesting processes. So, and then within Flaquet formalism, we have electronic structure of laser-dressed system. And when we theoretically want to understand how X-ray pulse interacts with this laser-dressed system, so just to briefly tell you how we do it theoretically. So the theoretical picture, you could say that we consider which transitions an X-ray probe pulse can induce within this laser-dressed system. So, and for details, I would refer to our paper here. So, and for us, X-ray pulse we describe within the perturbation theory. And here I'm going to show you the result and what we can learn from this X-ray optical wave mixing experiment. So what we propose is to consider Bragg diffraction from this laser-dressed system. So magnesium oxide has, it's very well known that it has several bright Bragg peaks, and one of these Bragg peaks is at this scattering vector G. 002. And then what we propose is that we not just look into the scattering angle, but we also do the spectroscopy of all photons in this scattering angle. So in the case of filter-free magnesium oxide, there will be a large Bragg peak at elastic Bragg peak, and there would be some inelastic scattering. But when we have this laser-dressed magnesium oxide, we found out that it will actually have side peaks to the main Bragg peak. So it means that there would be at frequency omega, omega is the driving frequency of a laser-dressed crystal, there will be a side peak, at 2 omega side peak, and so on. And within, and there will be also inelastic scattering that will be modulated, but we see that in principle it is not quite small. And theoretically, we prove that these side peaks have a very interesting information about electron dynamics. So we could prove that each side peak is actually the Fourier transform of the corresponding charge distribution. So what I mean by this? So the first order side, so when a crystal interacts with this driving field, there are some first order charge distribution that would lead to the first order polarization, or you could say the first order harmonic, for example. So, and this charge distribution oscillates with a frequency omega. So within Flaquet formalism, we are able to calculate this, and it is shown here. So, and you see it clearly shows the distribution, charge distribution due to as a dipole moment. And we could prove that this first order side peak is a corresponding Fourier transform of this charge distribution. Then the second order side peak is the Fourier transform of a second order charge distribution. Magnesium oxide is a crystal with the inversion symmetry, and it in principle doesn't have second order macroscopic polarization. But what we found that it indeed has second order microscopic polarization as shown here. So still charges rearranges within the unit cell, but it doesn't, you see, it doesn't have any dipole moment. So that means that you cannot measure this response macroscopically. But with this method, with X-rays, you get an access to this second order response, and that gives rise to this second order side peak to the main black peak. Yes. So here I also didn't mention this as the picture for the scattering vector parallel to the pump pulse polarization. So perpendicular to the pump pulse polarization, we also could see interesting selection rules for that. So the first all odd order side peaks disappear, even order side peaks remain, but from these pictures, in principle, one could understand how this could happen. We also, here in principle, we see that these side peaks strongly depend on the other parameters of the pump pulse. So, for example, if we derive the intensity of driving pulse, we could see that the first order side peak first at high intensities behaves non-perturbatively, but as the intensity of the laser dress field drops, it behaves perturbatively, meaning that perturbatively, I mean that the intensity of the first order side peaks goes linearly with the intensity of the driving pulse at these intensities, but at high intensities it has a non-perturbative behavior. The same is for the second order side peak. So at low intensities it's quadratic with the driving pulse, intensity of the driving pulse. At high intensity of the driving pulse, it's non-perturbative. So far I was speaking about so far I was speaking about time unresolved X-ray optical wave mixing, meaning that X-ray probe pulse is long in comparison to the cycle period of the driving pulse. But now the next question is what would happen if we want to be time resolved? So here the period of the laser-driven dynamics for omega 1.5 electron volts is 2.5 femtoseconds. And here we consider X-ray probe pulse of duration of 2 femtoseconds. So it is now subcycle resolved. And what happens is that in gray lines you see the regional side peaks as the X-ray probe pulse duration becomes shorter. These side peaks start to be broader, and becomes broader and broader, and then start to overlap. And overlap means that they start to interfere. And what we find out is that as soon as they start interfere, they become stop to be center-symmetric. So it means for scattering vector 002 and scattering vector 00-2, the signal is now different. And if we switch at a half cycle, so switch the time, then they also switch their positions. So to explain it better, I have this picture here of calculated electron dynamics of first order oscillations. So as I said, we are cycle resolved, but we can also, with this probe pulse duration, we can only resolve the first order oscillation in time. So I'm showing you the first order oscillation of magnesium oxide. So at this phase, first it has only electron probability current density. So probability current density at this. Then there's a quarter of phase difference, and the magnesium, so the charges start to be at maximum. So the charges start to rearrange. So when the oscillation continue, that the probability current density is at maximum at this phase, and then again after the quarter of a phase, the charge distribution switches its sign. So it's how the oscillation of charge distribution goes. And we see that at the time when the currents are at maximum, this break of the symmetry is maximum. When the probability current density is 0, then the signal is centrosymmetric. And we also, and this is not just an observation, we also could prove it theoretically that the signal is really related to the probability current density. And that actually you can extract this probability current density out of the signal. Here, what I'm showing on this picture is the difference between the signal at positive G and negative G, depending on the phase. And then we could show here that this is related. So this oscillation is proportional to the product between field-free density of magnesium oxide, or Fourier transform over field-free density of magnesium oxide, and the Fourier transform of electron current density. So that means that in principle, when one knows the field-free density of crystal which is driven, one can extract from this difference, one can extract the Fourier transform of microscopic electron current. So this brings me to my conclusions. So here first we found out that on a microscopic scale, the charge, so optically induced charge distribution can have very complex spatial structure, and that here we propose to image this complex spatial structure with X-rays that will act simultaneously with a driving pulse, and we show that this allows us to access the microscopic charge distributions. And both in time-resolved and time-unresolved case, we get an interesting insights about electron dynamics. And in the time-resolved or subcycle resolved case, we can get an access to the microscopic electron currents. Thank you.
Thank you very much, Daria, for your talk. So we have a few minutes for questions, please. May I ask a simple question, Daria? So your work is more theoretical. Could you compare, how do you compare your, let's say, results with experimental results in
Yes, so there's so far I have shown you theoretical results, but we have experimental collaborators on the time unresolved case. So that has been measured relatively recently at SACLA. So the preliminary results say that they do observe these side peaks to the main bragg peaks. So, and yes, and it's possible experimentally, yes.
I have another question. Do you focus your attention on octahedral coordination? So you have your central.
Sorry, this is I don't.
Try two other kind of coordinations.
No, so, sorry, this is not. So in our study, this is an infinite crystal. This is just a picture because to make a beautiful picture so that one can understand. I don't focus on the hydro.
Okay.
This is all in a bulk, yes.
Okay. More questions, please? If not, I would like to thank again to the speaker. So we finished this first part of the mini colloquium. Please don't miss the afternoon sessions engage in this mini colloquium where the flash talks and poster will be present. Now Harvey Amorim has information for us. Please, Harvey.
Thank you very much, Agustin. This is just an idea of the organization would like to take a general picture of the people of the attendee. I mean, many people have left already, but if you don't mind, if you can't open your video, it would be a pleasure to take a general picture of everyone. I'm not sure that everyone can open the video. Is okay? Okay. Okay, anyone else? Let me. Okay, so I go. Okay, so thank you very much, everybody. And okay, we'll take another one. So someone else are coming. So, okay. More people are coming, so I will wait a little bit, but okay, go ahead again. Okay, nice picture. Thank you very much. And just a little bit. Okay, so just in relation to the afternoon section, we would like to remind you that it would be very nice everyone here comes to this afternoon session. It would be at 17. No, it's 17. No, open your microphone, Austin, please.
5 p.m.
Okay, 5 p.m. And to the people is going to present their work there, the pre-recorded talk and poster. It would be nice if you come 15 minutes before 5 p.m. We will allow you to come into the session in order to share some information about how the session will go. Because we are discussing now how to do it because, okay, the organization says some general rules, but we are trying to be more open in order that people can talk, they can give their talk briefly, but by themselves without sharing without sending us the slide and so on. So please, all the people is going to present a flash talk should be 15 minutes before 5 p.m. in order to give you these tips, okay? And we invite everyone to be there at 5 p.m. in order to share not only this afternoon session, but also most of the people there can ask to the any question to the people that present the talk now in the morning, because we haven't too much time. And okay, it could be a good time for sharing information, to get in contact and so on. Okay, to get a closer communication between the different participants and so on. Anyway, at this moment we have a little more time, so if you want to share anything, if you want to make any question to the people, to any of the embodied talks or to any of the speakers, you can do it now. Or at least the session will be open for a little more time, a half hour more. So if you can share any information, you can't make any question to the speakers, you can do it now, okay? We have also a little bit time. If not, we see you in the afternoon, and it would be nice to see you there. Okay, and thank you very much to all the speakers.
Celine Moore has raised her hand. Please, Selena. I can unmute her. I can't. Selena, could you listen me? Could you unmute your microphone? Yes.
Okay, maybe now. Okay, finally. Sorry. Just a brief technical question for the flash presentation. So you mentioned that maybe we will be co-hosted and we can share our screen on, or how can we make it? We run the slides during the flash presentation.
Harvey, could you answer?
Okay, you mean for the afternoon session? Okay, the idea of the afternoon session was to the people send the presentation in all only one can share and so on. But in our case, as we don't have too many presentations that may be more confused, I think that I have to talk to Agustinho in class, but our feeling is that probably we can share, share your screen and you present your work by yourself without sharing with us the presentation.
Just because if the presentation is something like 10 minutes,
yes.
I guess the presenters will have like many slides. So, I mean, not as long as the pre-recorded talk, but like a summary in a sense.
Exactly. The important thing is that it is not to put the pre-recorded talk, but the idea is that you present, but in 10 minutes, not in 15 minutes, in a reduced time. But as I said, probably we don't have too much problem with the time. So we will see how things are going. But in principle, you should prepare for a 10-minute presentation. And depending on this, we will give you more time after the...
Okay. Yeah, we just know, because otherwise I would have prepared just a single slide. But
No, it's not necessarily a single slide. You can share more than one, and probably we will allow you to share their screen. So.
Okay, fine. Okay, thank you.
And the same with the other
sure.
Speakers.
Thanks.
So probably we can finish the session now.
Okay, yeah, we want to thank especially to the embodied speaker for the big effort, because this new modality of conference that we have now due to the pandemic situation. But special thanks to the embodied speakers and to the regular talks and pre-recorded talks, all of you, because it was difficult to make this in this way. And okay, thanks to everybody, and especially also to class and Agustinho for the effort of preparing all this.
Our pleasure.
See you then in the afternoon.
See you afternoon.
Thanks to everybody.
See you.
See you.
Harvard, you have tens tempo.